Hello there, and welcome back to the Sleep Science. Tonight, you're floating several hundred kilometers above Earth, weightless, watching a thin blue line glow against the velvet dark. The planet below you should be predictable at this hour. City lights steady, auroras behaving themselves near the poles, satellites humming along in polite silence. Instead, something flickers. Not dramatically, not in a Hollywood explosion kind of way. Just a faint, immeasurable tremor in the data, like the planet inhaled when it was supposed to exhale. You probably won't survive this. Relax. I mean that in the long geological sense. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as you settle in, tell me where you're listening from and what your local time is. Somewhere on this spinning globe, it's midnight. Somewhere else, it's nearly dawn. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're in a control room at NASA's Goddard Space Flight Center. The hour is late, technically early, and the fluorescent lights feel like they've been awake longer than anyone in the building. A bank of monitors displays real-time feeds from Earth-observing satellites, Terra, Aqua, the timed mission, the venerable fleet that has been circling your planet for decades. Since 1958, when NASA was officially established, the agency has kept a constant watch on the skies and the sphere beneath them. And tonight, those watchful eyes notice something odd. It begins with a whisper in the thermosphere, the layer of atmosphere that starts about 85 kilometers above your head and stretches hundreds of kilometers into space. Instruments record a subtle expansion, not enough to set off alarms, just enough to make a seasoned analyst squint at the screen and sip cold coffee with suspicion. The upper atmosphere naturally expands when heated by solar activity. That's textbook physics. Solar ultraviolet radiation pumps energy into sparse particles, and they spread out like guests at a too-warm party. But here's the twist. Solar activity tonight is quiet. The sun, that enormous nuclear furnace, 150 million kilometers away, is behaving. No significant flares. No dramatic coronal mass ejections. Space weather reports read like a calm forecast. Light solar winds, minor geomagnetic fluctuations. And yet the thermosphere seems to pulse as if it received a memo the sun forgot to send. You watch as numbers scroll. Density increases slightly. Satellite drag edges upward. That might sound dull, but for spacecraft operators, atmospheric drag is a very real concern. When the upper atmosphere puffs outward, it creates resistance. Satellites in low Earth orbit, like the International Space Station, have to periodically boost themselves higher to compensate. In fact, the ISS performs reboost maneuvers several times a year because of this very phenomenon. That's a mainstream, well-understood reality of orbital mechanics. Gravity pulls down, atmosphere tugs back, humans correct course. Tonight's change is small, but it's synchronized, across multiple instruments, across hemispheres. Historians still argue whether early space scientists in the 1960s fully grasped how dynamic the upper atmosphere could be. Back then, the first satellites occasionally decayed faster than predicted, surprising engineers who assumed space was emptier than it really is. The lesson was clear. Earth's atmosphere doesn't end neatly. It fades, breathes, shifts. And now, decades later, it seems to be breathing differently again. You lean closer to the data, and the anomaly appears shortly after local midnight in several regions. That timing catches attention. Human activity below tends to quiet at night. Less air traffic, slightly reduced industrial output, subtle temperature shifts at the surface. Could surface cooling ripple upward? Normally, the connection between the lower atmosphere and the thermosphere is complex but not immediate. The layers don't just text each other updates. Still, the models show a pattern. Around midnight, the upper atmosphere thickens just a little more than predicted. Then toward dawn, it relaxes, like a planet doing nocturnal yoga. A quirky tidbit floats through the room, half joke, half memory. In the early days of atmospheric science, some researchers speculated that large-scale human activity, like synchronized power usage, might measurably influence the ionosphere. The idea never gained solid footing, but it lingers as one of those Charming scientific what-ifs. You imagine millions of people charging their phones at once, and Earth sighing in response. If only planetary physics were that sensitive to your bedtime routine. The monitors blink again. A second instrument confirms the first, then a third. The anomaly isn't a glitch, it's a pattern. And patterns make scientists both excited and deeply suspicious. Well, you swivel your chair and glance at a visualization. Earth rendered in blues and greens, overlaid with faint lines representing magnetic fields. The magnetosphere, the invisible shield generated by your planet's molten iron core, deflects charged particles from the sun. Changes in this shield can influence the upper atmosphere. Tonight, the magnetometer readings show subtle fluctuations. Nothing dramatic, just enough to raise an eyebrow. There's a mainstream fact humming beneath all of this. Earth's magnetic field is not fixed. It drifts. The magnetic North Pole has been wandering from Canada towards Siberia at an accelerating pace over the last century. That movement is well documented, measured by satellites like ESA's Swarm mission and monitored closely by NASA collaborators. But the drift is gradual, measured in kilometers per year, not overnight pulses. So what is nudging the thermosphere? Historians still argue whether similar subtle shifts occurred in previous solar cycles and simply went unnoticed due to less precise instrumentation. That possibility hangs in the air like a polite ghost. Modern satellites are extraordinarily sensitive. Sometimes the better your instruments become, the more mysterious the ordinary appears. You glance at the clock. 2:17 a.m. Most of humanity is asleep, blissfully unaware that hundreds of kilometers above, molecules are spreading out just a bit more than expected. It's almost poetic. The planet performing a quiet adjustment while you dream about forgetting your locker combination from high school. A light joke passes between analysts. Maybe Earth just needed to stretch. After all, if you'd been spinning for 4.5 billion years, you'd want to roll your shoulders too. The room chuckles softly. Science, even serious science, survives on small humor at unreasonable hours. Yet beneath the levity is a hum of curiosity, because when multiple systems, thermal readings, density measurements, magnetic data, shift in gentle synchrony, you pay attention. NASA has been monitoring Earth from space for decades, building an archive so vast it feels like a planetary diary. And diaries are useful for spotting changes in tone. Tonight's entry reads, subtle expansion, synchronized, unexplained. You sit there, suspended between certainty and wonder. The numbers stabilize for a moment, then nudge upward again. Not alarming, not catastrophic, just unusual. And as the planet rotates toward dawn, you realize this is only the beginning of the pattern, an overnight shift that may have been happening quietly for longer than anyone noticed. The screens don't sleep, even if you wish they would. As Earth rolls gently beneath the satellite fleet, orbiting observatories continue their silent conversation. Us passing data down to ground stations scattered across continents like careful messengers. You imagine them whispering to one another in radio pulses, Terra murmuring to Aqua, timed chiming in from its higher perch. NOAA's weather satellites adding their steady commentary. Space may be quiet to your ears, but it's loud with information. The unusual shift doesn't stay isolated to one instrument. Within hours, atmospheric density readings from separate orbital paths begin aligning in a way that feels choreographed. Satellites in low Earth orbit, roughly 300 to 500 kilometers up, experience slightly increased drag at nearly the same local times. It's subtle, measurable in decimals and fourth significant figures, but consistent. Engineers notice their predictive models are off by just enough to be irritating. And in science, irritation is often the first clue. A mainstream fact anchors your thoughts. Satellites rely on exquisitely detailed atmospheric models like NRL MSISE00 to predict density in the upper atmosphere. These models incorporate solar flux, geomagnetic indices, and decades of historical measurements. They are usually reliable. Usually. When multiple spacecraft start reporting deviations from the model at the same nighttime window, analysts don't panic. They recalibrate, compare, verify. But they also lean forward in their chairs. On another monitor, you watch a global map flicker with color-coded overlays. Blues and purples indicate cooler regions, oranges and reds warmer ones. The thermosphere, despite its name, can reach temperatures above 1,500 degrees Celsius when energized by solar radiation. Yet because it's so thin, you wouldn't feel that heat in the way you imagine. Temperature here describes particle energy, not cozy warmth. And it's one of those counterintuitive space facts that makes you question everything you learned about hot and cold. Tonight, the temperature increase is mild but geographically widespread. What's peculiar is its timing. As cities dim and human activity slows, the upper atmosphere appears to stir. Historians still argue whether early atmospheric coupling theories underestimated the complexity between Earth's lower layers, the troposphere where weather lives, and the higher ionosphere and thermosphere. For years, these regions were studied almost separately, like siblings who rarely spoke. Now growing evidence suggests they're more connected than once believed. Waves generated by storms, mountain ranges, and even jet streams can propagate upward, transferring energy in slow, planetary ripples known as atmospheric gravity waves. Yes, gravity waves, not to be confused with gravitational waves from colliding black holes. Those are the dramatic cousins who flip tables at cosmic dinner parties. You watch as data from ground-based radar stations confirm something intriguing. The ionosphere's electron density shifts slightly during the same midnight window. On the ionosphere, stretching roughly 60 to 1,000 kilometers above you, is a charged region created when solar radiation strips electrons from atoms. It's crucial for radio communication because it reflects and refracts signals back toward Earth. Ham radio operators have known for over a century that the ionosphere behaves differently at night. Signals travel farther after sunset because ionization levels change. But this is layered atop the normal nightly cycle, an extra pulse, a synchronized adjustment. A quirky tidbit surfaces in a side discussion. In the 1970s, some researchers speculated that large-scale power grid usage might create measurable electromagnetic noise detectable from orbit. While modern studies show the effect is tiny compared to natural geomagnetic forces, the idea that your collective Netflix streaming could tickle the ionosphere is oddly delightful. Shouldn't you picture satellites rolling their metaphorical eyes as humanity queues up another late-night series? Still, the present data feels larger than digital chatter. The magnetometers on board several spacecraft show minor but coordinated fluctuations in the magnetic field lines surrounding Earth. Not a geomagnetic storm. Those are dramatic events often triggered by coronal mass ejections, capable of disrupting power grids and producing spectacular auroras. This is quieter. It's more like a magnetic murmur before dawn. You shift your attention to solar readings again. The sun rotates roughly every 27 days, carrying active regions across its face. Even when it appears calm, subtle variations in extreme ultraviolet radiation can influence the upper atmosphere. NASA's Solar Dynamics Observatory has been watching continuously since 2010, cataloging flares, sunspots, and magnetic loops with almost obsessive dedication. Tonight's solar flux index, however, shows no significant spike, so the satellites keep comparing notes. Orbit after orbit, they pass through the same geographic sectors at slightly different local times. Each pass becomes another data point, and as the Earth turns, the pattern repeats, most pronounced during local midnight to pre-dawn hours, tapering after sunrise. It's as if the planet's night side is responding to something unseen. Historians still argue whether subtle magnetospheric substorms, brief reconfigurations of Earth's magnetic tail caused by solar wind interactions, could produce such widespread thermospheric responses without obvious geomagnetic storm signatures. Substorms are common, almost routine, yet their full impact on upper atmospheric heating remains an active area of research. The magnetotail, stretched millions of kilometers away from the sun, can snap and reconnect in events that release bursts of energy. Usually, these manifest as intensified auroras. But what if smaller reconnections ripple more broadly than expected? On your display, auroral activity looks normal, mostly confined to high latitudes. Still, there's a faint brightening at slightly lower latitudes than average. Nothing dramatic enough to trend on social media, just enough to make space physicists exchange knowing looks. Meanwhile, what could GPS accuracy reports show tiny timing deviations? Nothing you'd notice while ordering food or navigating traffic. But at the scale of atomic clocks, accurate to billionths of a second, small ionospheric changes matter. Signals passing through a denser or differently structured ionosphere slow ever so slightly. Multiply that by thousands of satellites and millions of receivers, and you get a whisper of discrepancy. You imagine Earth wrapped in layers of invisible motion, neutral winds in the thermosphere reaching hundreds of meters per second, charged particles spiraling along magnetic field lines, gravity waves rising like slow ocean swells. All of it happening while most of humanity debates what snack to have before bed. A light joke breaks the tension in the control room. Perhaps Earth just prefers to do its stretching when nobody's watching. Like you attempting yoga in private, hoping no one sees you wobble, but the synchronization remains the real curiosity. Multiple satellites, independent instruments, matching midnight pulses, the night deepens, data continues to stream, and you begin to sense that this isn't an isolated flicker. It's a conversation unfolding across orbit, one that may reveal whether the shift is driven by the sun, the magnetosphere, the lower atmosphere, or something more complex weaving them together. The satellites keep circling, it's patient and tireless, comparing notes above your sleeping world. By the time the planet rotates another few degrees eastward, you start thinking of Earth less as a rock and more as a lung. From orbit, it already looks alive. Swirls of cloud curling like breath on cold glass. Auroras shimmering like nervous system sparks. But now the data gives that metaphor numbers. The thermosphere is expanding and contracting in a rhythm that feels almost respiratory. Not wildly, not catastrophically. Just enough that, if Earth had a chest, you'd swear you saw it rise. A mainstream truth anchors you. Earth's upper atmosphere naturally breathes in response to solar radiation. During the day, ultraviolet and X-ray energy heat the thermosphere, causing it to expand. At night, without direct solar input, it cools and contracts. This diurnal cycle has been measured for decades. Satellites have tracked it since the early space age. Seen when engineers learned the hard way that atmospheric density isn't static. But this shift doesn't fully match the textbook curve. The expansion appears slightly amplified during local midnight hours, when cooling should dominate. And it's not confined to one hemisphere or one longitude. The pattern seems global, as though the planet's breath has deepened while the sun looks the other way. You picture the thin air up there, mostly atomic oxygen at those altitudes, when individual atoms drifting far apart compared to the dense nitrogen and oxygen mix you inhale at sea level. In the thermosphere, particles can travel significant distances before colliding. It's less like air and more like a sparse crowd in a stadium parking lot after the game. And yet, even that sparse crowd responds to energy inputs with dramatic changes in scale. A slight temperature increase can cause the entire layer to puff outward by tens of kilometers. And that's not dramatic to you on the ground, but for satellites skimming the edge of space, it matters. Historians still argue whether long-term cooling of the thermosphere, linked to rising carbon dioxide concentrations, has altered how the upper atmosphere responds to short-term energy pulses. It sounds counterintuitive, but increased CO2 in the upper atmosphere actually enhances radiative cooling there, allowing heat to escape into space more efficiently. Over decades, this effect has led to a slight contraction trend in the thermosphere. NASA studies in the early 2000s documented this subtle shrinkage. So why would it now appear to expand more than expected at night? You lean into the models. Supercomputers simulate atmospheric tides, large-scale waves driven by solar heating, lunar gravitational pull, and even seasonal shifts. Yes, the moon contributes. Lunar atmospheric tides, though far weaker than ocean tides, still ripple upward through the layers. It's one of those delightful fringe-adjacent facts that sounds mystical, but is firmly grounded in physics. The moon doesn't just tug at oceans, it nudges the air itself. Tonight, the lunar phase is unremarkable. No supermoon theatrics, no eclipse drama, just the quiet gravitational companionship that's been ongoing for billions of years. Still, the data pulses. You examine cross-sectional graphs showing altitude versus density. Around midnight local time, while density increases slightly higher than predicted, then gradually settles as dawn approaches. It repeats across multiple orbits. The effect is small, but consistent enough to survive statistical smoothing. A quirky aside drifts through your mind. In the 19th century, some scientists believed Earth's atmosphere might extend infinitely into space, thinning but never truly ending. It took high-altitude balloon flights and eventually, on-air rockets to demonstrate the layered structure you now take for granted. If those early thinkers could see these graphs, they might feel vindicated in spirit. Earth's breadth stretching farther than expected. You glance at geomagnetic indices again. The KP index, a standard measure of geomagnetic activity, remains low. No storm-level disturbances. Yet more detailed magnetometer readings show micro-fluctuations in the magnetosphere's tail region. The magnetotail, here stretched away from the sun by solar wind pressure, stores energy like a taut rubber band. Occasionally, it snaps back in a process called magnetic reconnection, releasing energy that cascades toward the poles. Historians still argue whether smaller, frequent reconnection events, too subtle to trigger classic storm alerts, could collectively inject enough energy into the upper atmosphere to alter its nighttime cooling profile. The debate simmers in conference halls and journal articles. Tonight, it simmers in your control room. Meanwhile, neutral winds in the thermosphere, distinct from charged particle flows, are clocked at speeds exceeding 300 meters per second in some regions. That's over 1,000 kilometers per hour. You wouldn't feel it, of course. The air is too thin. But the idea of silent, supersonic breezes sweeping above you while you sleep is oddly poetic. You imagine the planet wrapped in invisible jet streams at the edge of space. If Earth is breathing, these winds are its circulatory system, redistributing energy from sunlit to darkened regions. And here's the strange part. The enhanced expansion appears strongest on the night side, where energy input should be minimal. It suggests redistribution rather than direct heating, like warmth being carried from day to night more efficiently than models anticipate. A light joke floats through the room. Maybe Earth installed a better thermostat overnight. Someone mutters about cosmic home improvement. The laughter is brief but welcome. Then comes another layer of data. Satellite laser ranging stations detect tiny changes in orbital decay rates. These stations bounce lasers off reflectors on satellites, measuring distance with centimeter precision. Over days and weeks, they can determine whether drag has increased. Preliminary calculations hint at a marginal uptick during the anomaly window. Well, mainstream physics says this: increased thermospheric density equals increased drag equals slightly faster orbital decay. No mystery there. The mystery lies in the timing and synchronization. You scroll back through archived datasets. Patterns similar to this appear faintly during previous solar minimum periods. That catches your attention. Solar minimum, when sunspot activity is low, often leads to a cooler, more contracted thermosphere overall. Yet some studies suggest that during deep minima, the upper atmosphere becomes more sensitive to even minor geomagnetic inputs. Historians still argue whether the unusually deep solar minimum of 2008 to 2009 permanently altered baseline thermospheric behavior. Some researchers propose that the system may have shifted into a subtly different equilibrium. Others remain skeptical. The planet continues rotating, unaware of your scrutiny. From your vantage point, imagined or real, you see city lights flicker off as dawn sweeps across continents. And as sunlight returns, the thermosphere warms in its usual way. The anomalous expansion blends back into the expected daytime curve. If you only looked at daylight data, you might miss it entirely. But night reveals it. Earth, in darkness, seems to breathe just a bit deeper than it used to. And as satellites continue their silent circuit, will you sense that this respiratory metaphor may not be poetic exaggeration? It may be the key to understanding how energy moves through the layered shell that protects every sleeping, dreaming human below. The deeper you follow the data, the more your attention drifts from air to magnetism, from breath to bone. Because wrapped around Earth, invisible but immensely powerful, is the magnetosphere, a vast teardrop-shaped shield carved into space by the solar wind. It extends tens of thousands of kilometers toward the sun, and stretches millions of kilometers behind the planet in a long magnetic tail. You don't see it when you look up at the night sky, but it is there, bending charged particles away, quietly guarding the atmosphere from erosion. And tonight, it's murmuring. A mainstream fact steadies you. Earth's magnetic field is generated by the geodynamo, the churning motion of molten iron and nickel in the outer core, about 3,000 kilometers beneath your feet. This motion creates electric currents, which in turn generate magnetic fields. It's a self-sustaining loop, and it has persisted for at least 3.5 billion years. Without it, solar wind would gradually strip away the atmosphere, as scientists believe happened to Mars. Yet the magnetosphere isn't rigid. It flexes and compresses under the constant pressure of solar wind, a stream of charged particles flowing outward from the sun at hundreds of kilometers per second. When solar wind intensifies, the magnetosphere shrinks slightly on the day side and stretches further on the night side. Tonight's solar wind readings are modest, speed steady, density unremarkable. No dramatic shock fronts racing toward Earth, and yet magnetometers aboard orbiting spacecraft register faint, coordinated tremors. As you watch a visualization of magnetic field lines, thin arcs looping from pole to pole, shimmering faintly as if drawn in electric ink. Around local midnight sectors, subtle fluctuations ripple through these lines. Not enough to classify as a geomagnetic storm. The KP index remains low, but sensitive instruments detect microvariations, tiny dips and surges in magnetic intensity. Historians still argue whether small-scale magnetospheric substorms have a greater cumulative heating effect on the thermosphere than once believed. Substorms are common, often triggered when magnetic reconnection occurs in the magnetotail. During reconnection, oppositely directed magnetic field lines snap and realign, releasing stored energy. This energy accelerates charged particles down toward the poles, igniting auroras. But not all reconnection events announce themselves with dazzling curtains of green light. Some are quieter, smaller, distributed. You glance at auroral imagery from polar orbiters. The auroral oval, the ring-shaped region around each magnetic pole where auroras most commonly appear, shows mild brightening. Nothing social media worthy. No neon sky spirals over Manhattan. Just slightly intensified emissions at higher latitudes. And yet, the timing aligns with the thermospheric expansion. How charged particles descending into the upper atmosphere deposit energy through collisions, heating the surrounding gases. That heating can cause localized expansion. But what you're seeing appears more globally distributed than a simple polar injection would explain. A quirky tidbit surfaces from geomagnetic history. In 1859, during the Carrington event, the most powerful geomagnetic storm ever recorded, telegraph systems sparked and failed, and auroras were visible near the equator. Some operators reportedly disconnected their power supplies and still managed to transmit messages using auroral-induced currents alone. That was magnetospheric chaos at its finest. Tonight is nothing like that. This is subtle, whispered. You focus on magnetometer data from multiple satellites at different orbital inclinations. One passes over the southern hemisphere midnight sector, another crosses the northern hemisphere slightly later. Both detect slight perturbations, small enough that a casual glance would dismiss them as noise. But they're not random. The perturbations follow a repeating local time pattern, peaking near midnight and diminishing toward dawn. That symmetry catches your analytical mind. Midnight is when the magnetotail is directly overhead relative to Earth's rotation. It's where stored magnetic energy tends to release during substorms. Historians still argue whether the magnetotail's dynamics are fully captured in existing models. Despite decades of missions, like NASA's Themis spacecraft, launched in 2007 specifically to study substorms, there are still gaps in understanding how energy transfer scales across the system. You imagine the magnetotail stretching away from Earth, buffeted by solar wind, storing tension like a cosmic slingshot. Occasionally it reconnects and snaps, sending ripples of charged particles inward. Perhaps tonight these snaps are smaller but more frequent, like the quiet crackle of static rather than a thunderclap. Meanwhile, ground-based magnetometer stations in Canada and Scandinavia detect faint geomagnetic pulsations known as Pi2 waves. These are often associated with substorm onset, The amplitudes are modest, but the timing aligns with the satellite observations. You picture invisible currents flowing along magnetic field lines, Birkeland currents, named after Christian Birkeland, or the Norwegian scientist who first proposed their existence in the early 20th century. For years, his ideas were controversial. Historians still argue whether his early laboratory experiments with magnetized spheres fully anticipated the complexity of real auroral currents, but satellites in the 1960s eventually confirmed he was largely correct. Those same field-aligned currents now surge gently, almost politely, between magnetosphere and ionosphere. And as they do, when energy seeps into the upper atmosphere, not explosively, gradually, enough to offset some of the expected nighttime cooling. You lean back and consider the coupling chain. Solar wind nudges magnetosphere, magnetotail reconnects, charged particles descend, currents flow, thermosphere warms slightly, density increases, satellites feel more drag. It's elegant, plausible. But is it sufficient? The global distribution of the expansion still seems broader than polar heating alone would suggest, where perhaps neutral winds redistribute the energy more efficiently than models predict. Perhaps gravity waves from below interact with magnetospheric inputs, amplifying the effect. A light joke circulates. Maybe Earth's magnetic field is just clearing its throat. Someone suggests offering it tea. The room smiles, but the curiosity deepens, because magnetic drift is also an ongoing reality. Earth's magnetic North Pole has been moving rapidly over the past few decades, forcing periodic updates to navigation models. Some researchers speculate that changes in core flow patterns might subtly influence magnetospheric geometry. Historians still argue whether recent acceleration in magnetic pole drifts signals a deeper restructuring within the outer core or simply a transient fluctuation. Either way, the magnetosphere you measure today is not identical to the one measured 50 years ago. And so, as midnight passes again over another longitude, the magnetic murmurs continue, small, synchronized, persistent. The planet turns, the magnetotail flexes, the thermosphere breathes a little deeper than expected, and you begin to suspect that this overnight shift may not belong to one layer alone, but to the entire interconnected system of Earth and space, whispering across invisible lines. By now, your gaze keeps drifting back to the sun. It's the obvious suspect. When anything in near-Earth space behaves strangely, you check the star first. When, after all, the sun is responsible for nearly every energetic process in the upper atmosphere. Solar ultraviolet radiation heats the thermosphere. Solar wind sculpts the magnetosphere. Solar flares can flood space with X-rays in minutes. Blaming the sun is a bit like blaming gravity. It's usually correct. And yet tonight, the sun looks almost innocent. A mainstream fact grounds you. The sun operates on an approximately 11-year solar cycle, oscillating between solar maximum, crowded with sunspots, sheer flares, and coronal mass ejections, and solar minimum when its surface appears calmer. Space weather forecasters track solar flux, particularly the F10.7 index, a measure of radio emissions correlated with ultraviolet output. This index feeds directly into atmospheric density models. The current readings: stable, no dramatic spikes, no hidden flare peeking around the limb. Solar observatories show a relatively placid photosphere, dotted with only modest active regions. You imagine the sun as a vast, simmering ocean of plasma, loops of magnetism rising and collapsing in slow arcs. It's never truly quiet. Even during minimum, small flares crackle and magnetic fields twist invisibly. But nothing in tonight's report suggests an energy surge strong enough to globally amplify the thermosphere's midnight expansion. Historians still argue whether subtle variations in extreme ultraviolet radiation, too small to dominate headlines, can still produce nonlinear effects in the upper atmosphere, especially during periods when baseline density is already low. Some models suggest that during deep solar minima, the thermosphere becomes more sensitive, like a thin blanket that reacts dramatically to even a slight tug. You pull up extreme ultraviolet (EUV) data from solar monitoring satellites. There are minor fluctuations, yes, but within expected bounds. No sharp upticks aligning precisely with the midnight anomaly. So if it's the sun, it's being very subtle about it. Then you remember high-speed solar wind streams. Unlike explosive coronal mass ejections, these streams originate from coronal holes, darker, cooler regions in the sun's corona where magnetic field lines open outward, allowing solar wind to escape more freely. When a high-speed stream reaches Earth, it can buffet the magnetosphere for days, producing recurring geomagnetic activity. A quirky historical tidbit drifts into view. In the 1970s, researchers first linked recurrent geomagnetic disturbances to coronal holes, long before space weather forecasting became routine. At the time, predicting solar wind patterns felt almost mystical. Today, it's standard practice. You check the solar wind speed charts. There has been a mild uptick over the past several days. Not dramatic, but sustained. Speeds creeping above average. Nothing storm level, but enough to keep the magnetosphere gently compressed. Could that steady pressure be priming the magnetotail for those subtle reconnection events you noticed earlier? Historians still argue whether sustained, moderate solar wind forcing can produce cumulative heating effects in the thermosphere that exceed predictions derived from short, intense storms. It's a matter of integration over time, like the difference between a quick sprint and a long, steady climb uphill. You picture the magnetosphere enduring a constant, patient push from the solar wind. Not a shove, more like someone leaning against a door. Over hours and days, that lean might subtly rearrange magnetic stresses. Meanwhile, solar radiation during the day heats the sunlit hemisphere as usual. But as Earth rotates into night, that stored energy doesn't simply vanish. A neutral winds redistribute it. Charged particles carry it along magnetic field lines. Perhaps the system is slightly out of equilibrium, taking longer to cool than models expect. A light joke slips into your thoughts. Maybe the sun sent a seen but not replying energy packet, technically active, emotionally distant. Back in the data, you compare the timing of solar wind fluctuations with the midnight density peaks. There's correlation, but not perfect alignment. The solar wind variations are broader, less sharply timed. The thermospheric pulses are more precisely locked to local midnight sectors. That precision nags at you. If solar input were solely responsible, you'd expect more direct synchronization with changes in solar radiation or wind pressure. Instead, the effect seems modulated by Earth's own rotation, suggesting an internal or magnetospheric mechanism layered atop solar forcing. You turn to another dataset, thermospheric composition. Instruments measure the ratio of atomic oxygen to molecular nitrogen at high altitudes. Changes in composition can affect density and cooling rates. Preliminary readings hint at slight composition shifts during the anomaly window, more atomic oxygen lingering longer into the night. Mainstream physics explains that atomic oxygen is more responsive to heating and expansion than heavier molecules. If its concentration remains elevated, density at certain altitudes increases. But why would composition shift specifically overnight? Historians still argue whether lower atmospheric dynamics, such as sudden stratospheric warmings, can cascade upward to alter thermospheric composition in ways not fully captured by current general circulation models. Sudden stratospheric warmings, primarily observed in winter polar regions, can disrupt jet streams and have been shown to influence the ionosphere days later. The coupling between layers is real, but still imperfectly mapped. You scroll through meteorological data. No major stratospheric events coincide exactly with the anomaly, though seasonal transitions are underway. The sun remains calm on your monitors, radiating with indifferent brilliance, and yet even a calm sun exerts enormous influence. The solar constant, the average energy Earth receives per square meter, is about 1,361 watts. A tiny fractional change in high-energy radiation can ripple through upper atmospheric chemistry. Will you imagine photons streaming outward, crossing 150 million kilometers in just over 8 minutes, striking the upper atmosphere and liberating electrons? It's a continuous bombardment, steady as breath. Maybe the answer isn't whether the sun is responsible, but how its steady output interacts with a magnetosphere and atmosphere that may be slightly tuned differently than before. Another midnight sector rotates into view. The density bump repeats, not larger, not smaller, consistent. You feel that peculiar mix of reassurance and intrigue. Reassurance because consistency means physics, not chaos. Intrigue because the physics isn't fully accounted for yet. The sun glows on your screen. Brilliant, complex, but not obviously guilty. And as Earth continues its quiet rotation, you realize the mystery may not lie in dramatic solar tantrums, but in the delicate balance between steady starlight, magnetic whispers, and a planet that seems to be holding on to nighttime warmth just a little longer than expected. High above your head, higher than airplanes, higher than weather, higher even than the auroras that tourists chase with thermal gloves and optimism, the ionosphere is shimmering. You don't see it directly. It's invisible to your eyes. But on the monitors, it looks like a living mosaic, shifting patches of electron density, glowing in false colors, greens, reds, electric blues. However, the ionosphere stretches roughly from 60 kilometers to more than 1,000 kilometers above Earth, overlapping with the thermosphere. It's created when solar radiation strips electrons from atoms and molecules, turning neutral air into plasma. Not sci-fi plasma, just lightly charged gas. Calm, mathematical, mostly cooperative. Mostly. A mainstream fact settles your thoughts. The ionosphere is divided into layers, D, E, and F, based on altitude and electron density. During the day, the F layer, especially the F2 region, becomes highly ionized and critical for long-distance radio communication. At night, ionization decreases as recombination processes allow electrons and ions to reunite. Electron density drops. Signals behave differently. This daily cycle has been measured since the early 20th century, when radio operators first noticed nighttime transmission quirks. But tonight's data adds an unexpected flourish to that familiar dance. Around local midnight, when the electron densities in the F region dip as expected, then rebound slightly, not dramatically, just enough to deviate from model forecasts. The rebound coincides almost perfectly with the thermospheric density bump you've been tracking. Historians still argue whether ionospheric midnight temperature maximum events, first documented in the 1960s, are fully understood. These events describe a curious phenomenon where temperatures in the upper atmosphere briefly increase near midnight instead of steadily cooling. Some attribute it to global-scale tidal winds redistributing energy from the dayside. Others argue magnetospheric inputs play a larger role than models suggest. You zoom into a longitudinal slice of the ionosphere. The electron density enhancement seems to follow geomagnetic coordinates more closely than geographic ones. That's interesting. I would suggest magnetic field alignment is influencing the pattern. Charged particles, after all, don't move freely in all directions. They spiral along magnetic field lines. If field-aligned currents intensify even slightly, they can alter local electron densities. A quirky tidbit floats into your awareness. In 1962, during the high-altitude nuclear test known as Starfish Prime, artificial radiation belts were briefly created around Earth, dramatically altering ionospheric conditions. Radio signals failed across parts of the Pacific. Satellites were damaged. It was a stark demonstration of how sensitive near-Earth plasma environments can be to energetic inputs. Thankfully, nothing remotely like that is happening now. Tonight's changes are gentle, almost polite. Still, the pattern persists. Ground-based ionosondes, radar-like instruments that bounce radio waves off the ionosphere, report slight anomalies in critical frequencies. So GPS signal delays show marginal increases during the same midnight window. If you were navigating a ship by satellite alone, you'd never notice. But atomic clocks and precision timing systems do. You imagine billions of signals crossing this charge layer every second. Navigation, financial transactions, weather data, slipping through a plasma that is just slightly denser than predicted. Historians still argue whether current ionospheric models adequately capture the coupling between neutral winds and plasma motion. Neutral winds in the thermosphere can drag ions with them through collisions, creating electric fields that redistribute plasma across latitudes. This process, called dynamo action, is complex and still under active research. Tonight, neutral wind measurements show enhanced equatorward flows during the anomaly period. That could help explain why electron density enhancements aren't confined to polar regions. You picture the ionosphere as a restless dancer responding to multiple partners at once. Solar radiation leading during the day, magnetospheric currents guiding at night, and neutral winds tugging gently from below. A light joke surfaces in your thoughts. If the ionosphere had a mood ring, it would be flashing mildly dramatic right now. But beneath the humor is genuine curiosity. Because the nighttime rebound in electron density appears synchronized across hemispheres, adjusting for magnetic conjugate points, locations connected by the same magnetic field lines. That symmetry hints strongly at magnetospheric involvement. You overlay thermospheric temperature maps with ionospheric electron density plots. The correspondence is not perfect, but it's compelling. Regions of slight temperature enhancement align with areas of plasma density increase. In mainstream physics offers a pathway: increased Joule heating. Joule heating occurs when electric currents flow through the ionosphere and encounter resistance. That resistance converts electrical energy into thermal energy, warming the surrounding neutral atmosphere. It's a well-established mechanism during geomagnetic activity, but typically significant Joule heating accompanies visible auroral intensification. Tonight's auroras are modest. Historians still argue whether low-level, persistent Joule heating during quiet geomagnetic conditions has been underestimated due to instrumentation limits in earlier decades. Modern satellites are far more sensitive. What once looked like background noise may now resolve into structure. You lean closer to a plot showing field-aligned current density. There, small but coherent enhancements around midnight local time. Nothing flashy, just steady. If currents increase slightly, even without a storm, they could produce distributed heating. That heating would expand the thermosphere locally, raising density and altering ionospheric recombination rates. And because Earth rotates beneath its magnetosphere, each longitude experiences its own midnight alignment with the magnetotail. That would naturally produce a repeating, rotation-locked pattern. You sit with that idea for a moment. It's elegant. It ties together magnetospheric murmurs, thermospheric breathing, and ionospheric rebounds. It doesn't require a solar tantrum. We're just a subtle rebalancing of currents flowing invisibly above. Outside the control room, dawn is breaking somewhere over an ocean. The ionosphere in that region transitions back into its daytime configuration, sunlight ionizing the upper layers, smoothing out the anomaly. But as night falls over another continent, the pattern returns, quiet, synchronized, patient. You imagine the planet wrapped in a thin shell of plasma, gently pulsing with magnetic rhythms while cities sleep below. A cosmic lullaby, measurable but unseen. And as another midnight sector rotates into view, the ionosphere resumes its restless dance, just a little more energetic than expected, hinting that the unusual shift may be less about a single cause and more about a delicate choreography between sun, magnetosphere, and a planet that refuses to be perfectly predictable. Midnight arrives again, not as a chime on a clock, but as a line sliding across a digital globe. You watch it sweep westward, and dividing day from night in a soft gradient. As that shadow line passes over continents and oceans, the data spikes return, faithful as a tide, precise as a metronome. If you were superstitious, you'd call it ritual, but you're not. You call it repeatability. And repeatability is where things get interesting. Ground stations begin reporting their own confirmations. Across Alaska, northern Canada, Scandinavia, and even equatorial observatories, instruments detect synchronized anomalies in upper atmospheric measurements. Fabry-Perot interferometers, delicate optical devices that measure thermospheric winds and temperatures by analyzing faint airglow emissions, register slight nighttime warming peaks. Independent, separate teams, same timing. A mainstream fact steadies the moment. Airglow is a real, measurable phenomenon. Even on nights without auroras, in the upper atmosphere emits faint light due to chemical reactions and recombination processes. It's far too dim for your casual stargazing eye, but sensitive cameras capture it easily. Variations in airglow intensity can reveal temperature and density changes in the thermosphere. Tonight, that glow subtly intensifies during the anomaly window. You imagine Earth wrapped in an invisible halo, brightening just a touch when the clock strikes magnetic midnight. Historians still argue whether earlier generations of ground-based measurements were precise enough to detect such subtle global synchronization. Before satellite constellations and worldwide instrument networks, Isolated observatories could miss patterns unfolding across hemispheres. It's possible this midnight pulse has been happening quietly for decades, only now resolving into clarity because the net of sensors has grown denser. As you scroll through data from incoherent scatter radars, massive installations that bounce powerful radio waves into the ionosphere to measure plasma properties, the returns confirm slight increases in ion temperature during the same time window. Not dramatic, but statistically significant. And then there are the magnetometers again. Ground-based stations detect faint geomagnetic pulsations, small oscillations in the magnetic field occurring every few minutes. Once these are known as PC and PI pulsations, categorized by their periods. They're common during substorm activity, but tonight they're present without the typical storm signatures. It's as if the planet is clearing its throat quietly instead of coughing loudly. A quirky anecdote drifts through your thoughts. During the early days of geomagnetism research in the 19th century, observatories would record magnetic field variations using ink pens attached to suspended magnets. The pens traced delicate squiggles on rotating paper drums. Scientists would later examine these inked lines for disturbances. You picture those Victorian researchers peering at faint midnight wiggles and wondering what invisible force was tugging at their instruments. Now, instead of ink and paper, you have terabytes of digital precision. The synchronized nature of the spikes is what unsettles and fascinates you. Each ground station experiences its local midnight at different universal times. Yet when you align the data by local time rather than UTC, the peaks stack neatly on top of one another. That alignment is not random. Historians still argue whether local time-dependent phenomena in the upper atmosphere are primarily driven by Earth's rotation interacting with magnetospheric geometry, or by internal atmospheric tides that propagate upward from below. The debate is ongoing because both mechanisms operate simultaneously. When you overlay atmospheric tidal models onto the midnight data, solar tides, driven by daily heating cycles, are well understood. Lunar tides are weaker but measurable. However, the amplitude of tonight's pulse exceeds what standard tidal models predict. Neutral wind data shows something curious. Around midnight, winds at high altitudes shift direction slightly more sharply than usual. Instead of a smooth transition, there's a brief acceleration phase. That could redistribute heat more effectively across latitudes. You imagine invisible rivers of air flowing at hundreds of meters per second, steering charged particles along magnetic highways. Meanwhile, satellite accelerometers, tiny devices that measure non-gravitational forces, detect minuscule increases in drag force during the spike window. Independent satellites confirm the effect. Different altitudes, same pattern. A light joke passes through your mind. If satellites had feelings, they'd be mildly annoyed right now. Excuse me, Earth, could you not thicken the atmosphere while I'm trying to orbit? But the pattern persists. One analyst compares the timing with global lightning data, just to rule out exotic coupling theories. After all, thunderstorms inject energy into the upper atmosphere via transient luminous events, sprites and jets that leap upward briefly. The correlation is weak. Lightning is too sporadic, too localized. Another compares seismic activity logs. Earthquakes can generate atmospheric gravity waves that propagate upward. No significant global seismic event aligns with the spike pattern. The midnight pulse remains stubbornly linked to geomagnetic alignment. You bring up a 3D model of Earth's magnetic field lines intersecting the atmosphere. At local midnight, certain regions align directly beneath the magnetotail's central plasma sheet, a region rich in energetic particles. Even mild enhancements in plasma sheet activity could inject energy downward along field lines. Historians still argue whether plasma sheet density variations during quiet solar wind conditions are more structured than previously believed. Recent missions suggest that what was once categorized as background plasma may have embedded waves and flows capable of influencing lower altitudes. You sit back and let the layers stack in your mind. Magnetotail reconnection, field-aligned currents, joule heating, neutral wind redistribution, ionospheric plasma drift, thermospheric expansion. It's not one spike. It's a chain reaction, subtle, synchronized, global. And perhaps the most intriguing part is its restraint. No blackouts, no satellite failures, no fiery skies. just small, consistent deviations from expectation. Another midnight line glides across the Pacific. Data rises, then falls, like a heartbeat. You begin to sense that the real discovery isn't a dramatic event, or is but a calibration shift. The models may need adjustment, not because physics has changed, but because your measurement resolution has sharpened. Still, the fact that it unfolds overnight, hidden from ordinary human awareness, gives it a quiet mystique. While you sleep, the planet's upper layers pulse gently in magnetic rhythm, and NASA's instruments, tireless and patient, continue to record every midnight breath. By the fourth consecutive night of watching the pattern repeat, could you begin doing what scientists always do when nature refuses to behave exactly as predicted? You question the models. Because models are the quiet backbone of everything you're seeing. They predict atmospheric density, ionospheric behavior, magnetic responses. They digest decades of measurements and translate them into equations that hum inside supercomputers. Without them, raw data would be just a blur of numbers. A mainstream fact anchors your thinking. Global circulation models of the upper atmosphere, like the thermosphere, ionosphere, electrodynamics general circulation model, TIEGCM, simulate how solar radiation, geomagnetic activity, chemistry, and winds interact. These models are continuously refined using observational data from satellites and ground stations. They are sophisticated, they are tested, and they are usually very good, usually. When you overlay predicted density curves against observed data during the midnight window, the discrepancy is small, on the order of a few percent, but persistent. In engineering terms, a few percent matters. For satellites skimming the edge of space, that can mean adjusting orbital decay estimates, recalibrating station-keeping maneuvers, rethinking drag coefficients. It's not catastrophic. It's inconvenient. And in science, inconvenience is often the birthplace of discovery. Once you scroll through historical archives, decades of thermospheric measurements from missions long retired. The Upper Atmosphere Research Satellite from the 1990s. Timed, launched in 2001, and still contributing. Champ and Grace satellites that carried sensitive accelerometers capable of measuring atmospheric drag with extraordinary precision. Historians still argue whether long-term climate trends have subtly altered upper atmospheric baseline conditions in ways that complicate short-term anomaly detection. Rising greenhouse gases cool and contract the thermosphere over decades, a well-documented effect. But that long-term contraction might amplify relative responses to geomagnetic or tidal inputs. In other words, if the blanket has grown thinner over time, even a modest energy pulse feels more noticeable. You examine temperature trends over the past 20 years. There is indeed a gradual cooling trend in the thermosphere consistent with increased carbon dioxide radiative cooling. That's textbook atmospheric physics, counterintuitive but solid. More CO2 at high altitudes enhances infrared emission to space, allowing heat to escape more efficiently. But the current anomaly isn't a long-term drift. It's a rhythmic overnight swell layered atop that background trend. A quirky historical note surfaces. In the early 20th century, before satellites, scientists inferred upper atmospheric behavior indirectly from meteor trails. When meteors streak through the sky, they ionize air along their paths. By analyzing how long those ionized trails persist, researchers could estimate upper atmospheric density. It was atmospheric science by celestial graffiti. Imagine trying to detect a global midnight pulse using only falling space rocks. You almost smile at how far instrumentation has come. You feed the latest week of data into updated model runs, adjusting parameters for minor increases in Joule heating and neutral wind acceleration. The simulated curves align better, but not perfectly. There remains a slight lag between predicted and observed peaks. Historians still argue whether coupling between the lower atmosphere and the thermosphere is adequately represented in most global models. Atmospheric gravity waves, generated by storms, jet streams, and even mountain ranges, propagate upward, breaking in the upper atmosphere and depositing energy. Their cumulative effect can alter wind patterns and temperatures significantly. Recent studies suggest that gravity wave activity may intensify during seasonal transitions. You check the calendar. Indeed, you're near a transitional period between seasons in one hemisphere. That could amplify upward energy transfer. As you overlay satellite cloud top temperature data with gravity wave proxies, there are hints of enhanced wave activity over certain continental regions, but the midnight synchronization still aligns more cleanly with geomagnetic coordinates than with storm clusters. A light joke drifts into your thinking. Maybe Earth just updated its firmware and forgot to send the patch notes. Yet the possibility lingers that what you're witnessing is not a new phenomenon, but a newly visible one. Model resolution has improved dramatically in the past decade. Data assimilation techniques now ingest real-time measurements into simulations, refining outputs dynamically. Subtle patterns that would have drowned in statistical noise 20 years ago now rise above it. You revisit archived data sets from a previous solar minimum. When aligned by local time and filtered carefully, faint hints of a similar midnight density bump appear. It wasn't flagged then. Perhaps it was dismissed as measurement uncertainty. Historians still argue whether scientific progress sometimes reveals variability that was always present but masked by coarser instruments. The line between new event and new detection capability is often blurry. You sit quietly watching another midnight sector roll into alignment. The density rises again. The ionosphere shimmers slightly brighter. Magnetometers twitch gently. The pattern is steady, reproducible, global, not escalating, not fading, and that steadiness begins to feel less like anomaly and more like adjustment. Perhaps the model slightly underestimated low-level magnetospheric heating during quiet solar wind conditions. Perhaps they oversimplified neutral wind redistribution. Perhaps atmospheric tides interact more strongly with geomagnetic geometry than previously quantified. The beauty and mild frustration of Earth system science is that everything connects. Solar radiation influences chemistry. Shooting chemistry affects temperature. Temperature drives winds. Winds redistribute plasma. Plasma alters electric fields. Electric fields feed back into heating. It's a loop layered upon loops. Another comparison chart appears on your screen, this time plotting satellite drag anomalies against geomagnetic pulsation amplitude. The correlation coefficient isn't perfect, but it's statistically meaningful. You lean back, letting the hum of equipment fill the silence. Outside, somewhere beneath the invisible pulse, people are brushing their teeth, turning off lamps, scrolling through their last messages of the night. They have no idea that above them, the upper atmosphere is performing a small but synchronized adjustment, one that NASA is quietly cataloging in spreadsheets and code. You realize the question may be shifting from what is causing this to how long has this been happening? And perhaps even more intriguingly, what else have we not noticed yet? Because when models and measurements diverge, even slightly, it's an invitation. An invitation to refine, to recalibrate, to listen more closely to a planet that seems to breathe differently after midnight. As the data continues its quiet repetition, your attention drifts north, far north, where the sky itself sometimes betrays the invisible choreography above. Because if energy is flowing differently through the magnetosphere and ionosphere, the auroras will know. A mainstream fact steadies you. Auroras occur when charged particles from the magnetosphere collide with atoms and molecules in Earth's upper atmosphere, exciting them. When those atoms relax back to lower energy states, they emit light, green from oxygen around 100 to 300 kilometers up, red from higher altitude oxygen, and purples and blues from nitrogen. The auroral oval typically hugs high latitudes centered around the magnetic poles. Tonight's satellite imagery shows something subtle but intriguing. The auroral oval appears slightly expanded equatorward during the midnight window, not dramatically, not storm level, but by a measurable margin. The boundary shifts a degree or two lower in geomagnetic latitude before retreating again toward dawn. To the casual observer on the ground, it might mean a faint green shimmer visible a little farther south than forecast. To you, it's confirmation that energy input from the magnetotail may be spreading wider than models anticipate. You imagine standing beneath that sky, cold air biting your cheeks, stars crisp overhead, and noticing that the aurora seems just a little more persistent than usual. One not spectacular, just lingering. Historians still argue whether subtle expansions of the auroral oval during geomagnetically quiet periods were historically underreported. because human observers tend to document only the most dramatic displays. Before all-sky cameras and satellite ultraviolet imaging, faint auroras might have gone unnoticed in sparsely populated polar regions. Now, with instruments like NASA's IMAGE mission in the early 2000s and subsequent polar orbiting satellites, global auroral imaging became routine. Tonight's ultraviolet maps show a slightly brighter ring, especially in the midnight sector. The timing aligns again with the thermospheric density peaks. You overlay maps of Joule heating estimates derived from electric field measurements. Regions beneath the expanded auroral oval show modest increases in energy deposition. Nothing that would alarm power grid operators, but enough to warm the upper atmosphere locally. And here's the interesting part. Neutral winds don't respect strict geographic boundaries. Heat deposited at high latitudes can be redistributed toward mid-latitudes by high-altitude wind systems. The thermosphere behaves like a thin, fast-moving ocean. A quirky historical note surfaces. In 1770, a series of intense auroral events were recorded across East Asia and Europe, were described in diaries as red vapors filling the heavens. Some historians suggest that event rivaled the Carrington storm in intensity, but documentation was fragmented, scattered across journals and letters. Today, such an event would be captured instantly by satellites, smartphones, and automated sensors. You're grateful that tonight's auroral expansion is modest. Dramatic auroras are beautiful, but they usually come with disruptive geomagnetic storms. Historians still argue whether the size of the auroral oval directly correlates with total thermospheric heating, or whether distributed electric fields can deposit comparable energy without dramatically enlarging the visible aurora. In other words, can the system warm more quietly than it glows? The data suggests yes. You zoom into particle flux measurements from satellites traversing the plasma sheet. There's a slight uptick in medium energy electron precipitation during the midnight window. Not extreme, just elevated compared to baseline. Those electrons spiral down magnetic field lines, colliding with atmospheric constituents, contributing both to auroral emissions and to heating. You picture the magnetotail releasing tiny packets of energy, like someone gently tapping a drum instead of striking it hard. Each tap sends ripples inward. Meanwhile, ground-based all-sky cameras confirm that auroral arcs during the anomaly period are marginally thicker, subtle widening of luminous bands before they fade toward dawn. A light joke slips into your thoughts. It's as if the aurora is stretching its arms a little wider before going back to bed. But the implications are technical. Even small expansions of the auroral oval mean electric currents are flowing across a slightly broader region of the ionosphere. Those currents generate Joule heating, which feeds into the thermospheric expansion you've been tracking. Another layer of data appears. Satellite measurements of nitric oxide concentration in the upper atmosphere. Nitric oxide is produced during energetic particle precipitation and plays a key role in thermospheric cooling by radiating infrared energy. Interestingly, its concentration increases slightly after the midnight pulses, suggesting that the atmosphere is compensating, warming briefly, then activating cooling pathways. Historians still argue whether nitric oxide variability during quiet geomagnetic conditions has been adequately incorporated into long-term thermospheric climate models. It's one of those niche but crucial details that can shift temperature predictions by small yet meaningful margins. You watch as another midnight passes over northern Canada. The auroral oval brightens just a touch, then recedes. Thermospheric density ticks upward, then settles. The pattern is so consistent now that it feels almost ceremonial. Energy from the magnetotail flows inward. Auroras widen slightly, currents intensify modestly. The thermosphere warms, density increases. Neutral winds redistribute that warmth. By dawn, sunlight reasserts dominance, smoothing the curve, and then it begins again somewhere else on the globe. You lean back and consider how invisible most of this is to the world below. No headlines, no flashing warnings. Just a planet and its magnetic shield adjusting quietly in the dark. The subtle expansion of the auroral oval feels like a visual signature of the larger shift. Proof that the overnight anomaly isn't a random blip in instrumentation, but a coordinated response in the space atmosphere system. Above the poles, curtains of light ripple faintly wider than expected, And beneath those luminous arcs, Earth's upper layers continue their slightly deeper midnight breath. While your eyes have been fixed on the sky, another dataset waits patiently below. Quieter, heavier, and far less flashy than auroras. The oceans. At first, it seems almost absurd to connect midnight pulses in the thermosphere with anything happening in the sea. The layers are separated by dozens of kilometers of atmosphere, by gravity, by entirely different physical regimes. And yet Earth is a coupled system. Tug one thread and something else may tremble. A mainstream fact steadies you. Satellites like Jason 3 and Sentinel-6 use radar altimetry to measure global sea level with millimeter precision. By bouncing microwave pulses off the ocean surface and timing their return, scientists can detect subtle changes in sea height caused by tides, temperature, and circulation patterns. Over decades, these missions have documented global mean sea level rise with extraordinary accuracy. Tonight's anomaly is not sea level rise. It's much smaller than that. But when analysts align altimetry data by local time, just as they did with thermospheric density, something curious appears. A barely perceptible modulation in upper ocean surface height during the midnight window in certain regions. You blink at the graph. The variation is tiny, fractions of a millimeter. It could easily be dismissed as tidal noise, but the timing matches. Historians still argue whether atmospheric pressure fluctuations at high altitudes can indirectly influence ocean surface height through complex coupling mechanisms. The most obvious connection is the inverted barometer effect. When atmospheric pressure increases at the surface, sea level decreases slightly beneath it, and vice versa. However, the thermospheric changes you're tracking occur far above the weather layer. So how could space touch the sea? You dig deeper. What's the key may not be direct pressure, but energy redistribution. Enhanced Joule heating in the ionosphere can alter upper atmospheric circulation, which can subtly influence lower atmospheric tides. Those tides, in turn, propagate downward and horizontally, interacting with oceanic tidal systems. It sounds like a long chain, and it is, but Earth's systems are notoriously interconnected. A quirky historical aside drifts into your mind. In the late 1800s, scientists debated whether the moon's gravitational pull could measurably deform the solid Earth itself. Today, we know it does. Earth experiences solid body tides of up to about 30 centimeters. The ground beneath your feet rises and falls gently each day, though you never feel it. Compared to that, a millimeter-scale ocean modulation tied to atmospheric coupling is almost shy. You overlay ocean tidal models with the midnight thermospheric pulse. In some coastal regions, the predicted tidal amplitude aligns constructively with the anomaly window, slightly amplifying the observed effect. In other areas, it cancels out. Historians still argue whether global ocean circulation models fully account for subtle atmospheric tide influences driven from above rather than below. Most models focus on gravitational forcing and wind stress at the surface. While the idea that space weather-driven atmospheric tides might ripple downward into measurable ocean responses remains an active niche of research. You're careful here. Correlation does not mean causation. The ocean is noisy. Currents, waves, pressure systems, lunar tides all overlap in complex patterns. But the coincidence is intriguing enough that you flag it. Meanwhile, sea surface temperature data shows no unusual midnight spikes. That's reassuring. If there were large-scale energy injections reaching the troposphere, you'd expect clearer thermal signatures. Instead, the possible link appears more rhythmic than thermal, like a slight modulation layered onto existing tidal oscillations. You picture Earth as a layered orchestra. The magnetosphere plucks a faint string at midnight. The ionosphere vibrates. The thermosphere hums. Atmospheric tides shift subtly. And somewhere far below, the ocean responds with the faintest change in pitch. A light joke floats through your thoughts. If the planet were any more interconnected, it would need group therapy. Back in the data, you examine satellite gravimetry from missions like GRACE and GRACE-FO, which measure tiny changes in Earth's gravity field caused by mass redistribution, water moving across continents, ice sheets melting, oceans sloshing. There's no significant gravity anomaly aligned with the midnight pulses. That suggests any oceanic response is extremely shallow, Surface level, not a deep redistribution of mass. Historians still argue whether short-term space weather variability can measurably influence lower atmospheric pressure patterns. Some studies suggest weak statistical links between geomagnetic activity in certain weather regimes, though the mechanisms remain debated and controversial. You tread carefully. The last thing you want is to overstate the coupling. Still, the fact that the midnight thermospheric expansion repeats so consistently raises the possibility that even distant layers may feel its echo. Another midnight sweeps across the Pacific. The thermosphere expands slightly. Auroras widen a touch. Magnetometers twitch. And ocean altimeters register a whisper of surface modulation in select regions. It's not dramatic. It won't flood coastlines. It won't alter shipping routes. But it reinforces the central realization forming in your mind. This is not an isolated atmospheric quirk. It's systemic, a small synchronized adjustment linking magnetosphere, ionosphere, thermosphere, and perhaps, faintly, the ocean surface. You lean back and imagine the planet from space, blue oceans, white clouds, green continents, all wrapped in invisible magnetic lines and shimmering plasma. Every layer in conversation, even if the voices are soft. While most of humanity sleeps, that conversation continues, midnight after midnight, and NASA's instruments, patient and precise, keep listening as the sea below responds with the faintest ripple to a pulse born far above the clouds. Just when you think you've traced every earthly connection, your gaze drifts outward, past the magnetosphere, past the solar wind, into the broader cosmic neighborhood. Because Earth does not drift through empty space. It moves through a subtle rain of high-energy particles known as cosmic rays, atomic nuclei accelerated by distant supernovae, flung across the galaxy at nearly the speed of light. They are ancient travelers. Some began their journey millions of years ago, long before humans learned to build satellites to measure them. A mainstream fact steadies your thoughts. Cosmic ray intensity near Earth is partially modulated by solar activity. During solar maximum, the strengthened solar magnetic field deflects more galactic cosmic rays, reducing their intensity near Earth. During solar minimum, more cosmic rays penetrate the inner solar system. This inverse relationship has been measured for decades using neutron monitors on the ground. And right now, solar activity is relatively calm. You pull up neutron monitor data from stations in Oulu, Finland, and McMurdo, Antarctica, two of the most reliable long-term cosmic ray observatories. There's a modest uptick in counts compared to solar maximum years. That's expected during quieter solar conditions. But over the past several nights, there's been a tiny synchronized increase in high-energy particle flux during the same midnight window you've been tracking. Not dramatic, not a storm, just a fractional rise. Historians still argue whether short-term cosmic ray variations, known as four-Bush decreases and their smaller counterparts, can influence upper atmospheric chemistry in measurable ways. Large four-Bush decreases are tied to coronal mass ejections, sweeping cosmic rays aside. But subtle increases, particularly during quiet solar wind conditions, are less understood in terms of immediate atmospheric impact. Cosmic rays penetrate deep into the atmosphere, ionizing molecules along their paths. Now, in the lower atmosphere, they've even been hypothesized controversially to influence cloud formation by seeding aerosols. That debate remains unsettled, but in the upper atmosphere, additional ionization from cosmic rays is more straightforward. You overlay cosmic ray intensity data with ionospheric electron density plots. The correlation is faint but intriguing. Midnight sectors show slightly enhanced ionization rates coinciding with the cosmic ray uptick. Sure, it's small, far weaker than solar-driven ionization during the day. But at night, when solar radiation ceases, even minor additional ionization stands out more clearly. A quirky historical tidbit drifts through your mind. In the early 1900s, physicist Victor Hess discovered cosmic rays by ascending in a balloon with an electroscope, measuring increased radiation at higher altitudes. His daring flights earned him a Nobel Prize. Imagine explaining to him that, over a century later, you'd be correlating his discovery with midnight thermospheric density pulses. You almost feel like you're standing in that balloon basket, drifting upward into invisible particle showers. Historians still argue whether cosmic ray modulation during quiet geomagnetic conditions can subtly alter the conductivity of the ionosphere, enough to influence global electric circuits. The global electric circuit, a continuous flow of electrical current between Earth's surface and the ionosphere, is maintained by thunderstorms worldwide. Variations in ionospheric conductivity could slightly adjust that current, and if conductivity shifts, electric fields may shift. You glance at electric field measurements from low Earth orbit satellites. During the anomaly window, there are slight enhancements in certain longitudinal sectors. Again, nothing dramatic, but aligned. As could increased cosmic ray ionization enhance nighttime conductivity just enough to modify current flow, adding to Joule heating and thermospheric expansion? The chain is delicate, but physically plausible. You imagine Earth moving through a slightly denser patch of galactic particle flux, like a car driving through a light mist instead of dry air. The change wouldn't be dramatic, but over time it could subtly alter surface conditions. Meanwhile, Earth's magnetic field filters cosmic rays unevenly. High latitudes receive more penetration due to open magnetic field lines near the poles. That aligns with the auroral expansion you've observed. Perhaps cosmic ray influx is reinforcing magnetospheric particle precipitation in those regions. A light joke slips through your thoughts. Space really doesn't believe in quiet hours, does it? The magnetosphere, solar wind, and cosmic rays form a layered shield and shower system. When solar wind is steady but not overpowering, galactic cosmic rays can seep in slightly more freely. During local midnight, when regions rotate into optimal alignment with the magnetotail and polar cusps, penetration efficiency might shift subtly. Historians still argue whether Earth's passage through small-scale interplanetary magnetic field variations, tiny folds and waves in the heliosphere, could produce localized cosmic ray flux changes synchronized with planetary rotation. It's an emerging area of heliophysics research, far from fully resolved. You check heliospheric data from spacecraft stationed upstream of Earth, like the DS Cover satellite at the L1 Lagrange point. Solar wind parameters remain steady, but small fluctuations in the interplanetary magnetic field orientation appear during the anomaly periods. Orientation matters. When the interplanetary magnetic field aligns southward relative to Earth's field, reconnection efficiency increases. Even modest southward turnings can enhance energy transfer into the magnetosphere. You connect the dots slowly. Slight interplanetary magnetic field shifts to enhance magnetotail reconnection, to mild auroral expansion, to increased Joule heating, to thermospheric expansion, to small density bump. Cosmic rays might not be the primary driver, but they could be an amplifier, subtly enhancing nighttime ionization. You sit quietly with the realization that the anomaly may not have a single cause at all. It may be the cumulative effect of several small influences aligning in phase, like instruments in an orchestra briefly synchronizing on a particular chord. Another midnight line slides across the Atlantic. Cosmic ray counts tick upward slightly. Electron densities rebound. Thermospheric temperatures nudge higher. Auroras widen just a touch. The pattern remains steady, subtle, consistent. Watch, you feel less like you're chasing a mystery and more like you're witnessing a finely tuned system revealing one of its quieter rhythms. Above you, beyond the sun, beyond the heliosphere, distant supernova remnants continue to accelerate particles into space. Some of those particles reach Earth, and in the stillness of midnight, their ancient energy may be contributing, just a little, to the planet's slightly deeper breath. At this point, you're not just thinking about particles and plasma. You're thinking about satellites, because whenever the upper atmosphere changes, even slightly, the first to feel it are the machines you've placed in orbit. They are the canaries in this very high-altitude coal mine, except instead of chirping, they send telemetry packets at 28,000 kilometers per hour. A mainstream fact grounds you. Satellites in low Earth orbit experience atmospheric drag due to collisions with thermospheric particles. Even at 400 kilometers altitude, in where the International Space Station orbits, the atmosphere is thin but not absent. Drag gradually slows spacecraft, causing their orbits to decay unless periodic reboost maneuvers are performed. This is routine, predictable, accounted for, unless density changes unexpectedly. You pull up orbital tracking data from several Earth-observing satellites. Over the past week, operators have noticed slightly higher than predicted drag coefficients during local midnight passes. Nothing mission-threatening, but enough to require small adjustments in orbital models. The International Space Station itself experiences measurable variations in drag depending on solar activity. During strong geomagnetic storms, the atmosphere can expand dramatically, increasing drag and lowering the station's altitude more quickly than planned. That has happened before. This is not that. This is quieter. Historians still argue whether improvements in accelerometer sensitivity over the past 2 decades have revealed drag fluctuations that were previously masked by instrument noise. Missions like CHAMP and GRACE carried ultra-precise accelerometers capable of detecting tiny non-gravitational forces. Their data revolutionized thermospheric density modeling. Now modern satellites continue that legacy, with even better calibration. You compare predicted versus observed orbital decay rates. When the difference is small but systematic. During the midnight window, decay accelerates slightly. By dawn, it returns to baseline. It's almost polite. Like the atmosphere is tapping satellites gently on the shoulder and saying, "Just so you know, I'm here." A quirky anecdote surfaces. In 1979, NASA's Skylab space station re-entered Earth's atmosphere earlier than expected, partly because increased solar activity heated and expanded the upper atmosphere, increasing drag. And engineers had underestimated how much the sun could puff up the thermosphere. Pieces of Skylab scattered over Western Australia, and somewhere a farmer probably gained the world's most inconvenient lawn ornament. Tonight's changes are nowhere near Skylab level dramatic, but they are measurable. You glance at GPS satellite performance logs. GPS satellites orbit much higher, around 20,200 kilometers, well above the thermosphere. They don't feel drag in the same way. But their signals pass through the ionosphere twice. Once on the way down, once on the way back up if reflected. Slight changes in ionospheric electron density can introduce small timing delays in GPS signals. These delays are normally corrected using dual-frequency techniques. Still, during the anomaly window, timing residuals increase slightly before correction algorithms compensate. Historians still argue whether small, persistent ionospheric variability during geomagnetically quiet periods has cumulative effects on high-precision timing systems, such as those used in financial markets or power grid synchronization. Most systems are robust, but when you're measuring time to billionths of a second, even minor plasma fluctuations matter. You imagine billions of devices, phones, ships, aircraft, autonomous tractors, quietly trusting signals that have passed through a slightly thicker ionosphere than expected. Radio communications show similar subtlety. High-frequency radio operators report marginal improvements in nighttime propagation range during the anomaly window, consistent with enhanced F-region electron density. Nothing that would trend on hobbyist forums as epic skip conditions. Just slightly clearer, long-distance chatter. A light joke drifts through your mind. Somewhere, a late-night radio enthusiast might be unknowingly benefiting from magnetotail physics. You review satellite attitude control logs. Some low-Earth orbit spacecraft report tiny increases in torque due to atmospheric variability. Nothing destabilizing, but noticeable enough that onboard control systems adjust reaction wheels a bit more frequently. It's fascinating how sensitive these machines are, how even a few percent increase in thermospheric density becomes visible in mechanical responses. Historians still argue whether the long-term contraction of the thermosphere due to greenhouse gas cooling has actually extended satellite lifetimes overall by reducing average drag. Some studies suggest yes. A thinner upper atmosphere means debris and defunct satellites linger longer before re-entering. That's good for mission duration, but problematic for space debris management. You consider that irony for a moment. A cooler thermosphere may help satellites stay up longer, but it also means space junk sticks around. Tonight's midnight pulse slightly reverses that contraction trend, temporarily thickening the atmosphere. You overlay space debris tracking data, no unusual re-entries, no collision warnings triggered by density miscalculations. Everything remains well within operational margins. And yet, the fact that technology feels the shift, even gently, confirms its physical reality. This isn't just a graph artifact. Satellites are physically encountering more particles during those midnight passes. The atmosphere is objectively denser. You imagine a small Earth-observing satellite slicing through the thin air at orbital velocity, its surface encountering a few more oxygen atoms per cubic centimeter than expected. Those atoms collide, transferring tiny amounts of momentum. Multiply that by billions of collisions, and orbital energy decreases just a bit faster. Surely it's microscopic physics producing macroscopic consequences. Another midnight rotates into alignment. Drag increases, ionization rebounds. Electric fields intensify slightly. Then, as sunlight creeps over the horizon, the anomaly dissolves into the daytime pattern. You sit back and reflect on the elegance of it all. A chain of cosmic and magnetic events, subtle and distributed, influencing everything from auroral glow to satellite orbit predictions. Technology feels the strain, but only barely. And perhaps that's the most remarkable part. This overnight shift is real enough to measure, to adjust for, to study, yet gentle enough that the world below continues sleeping peacefully, unaware that above them, their machines are gliding through air that has grown just a little thicker in the dark. By now, the pattern feels less like a glitch and more like a signature. So you do what any careful observer does when confronted with a repeating mystery. You look backward. You dive into archives. And decades of data sit quietly on servers, stretching back through multiple solar cycles, geomagnetic storms, quiet years, noisy years. The satellites change. The instruments improve. But the planet keeps turning, offering midnight after midnight for analysis. A mainstream fact steadies your approach. Continuous thermospheric measurements with meaningful precision have existed since the 1960s. But global, when high-resolution coverage became far more robust in the late 1990s and early 2000s, with missions like CHAMP, GRACE, and TIMED. Before that, data was patchier, valuable, but less synchronized. You align historical data sets by local time instead of universal time, just as you did with the current anomaly. It's tedious work, filtering solar storm days, excluding major geomagnetic disturbances, isolating geomagnetically quiet intervals. And then faintly you see it, not as clearly as today. Not as consistently, but there are hints. Subtle midnight density enhancements during certain quiet solar wind periods, especially near deep solar minima. Historians still argue whether the unusually prolonged solar minimum of 2008 to 2009 fundamentally shifted thermospheric baseline conditions. That minimum was deeper and longer than many predicted, producing some of the lowest thermospheric densities measured in the space age. Satellites experience record low drag. Some researchers propose that the upper atmosphere had entered a slightly altered equilibrium state. You overlay data from that era. There it is again, a small local time-locked bump. It wasn't flagged prominently in published summaries. It may have been absorbed into model uncertainty margins. But in hindsight, with modern processing techniques, it stands out more clearly. A quirky historical note drifts into your thoughts. In 1930, when Pluto was discovered, our astronomers initially thought it might be as massive as Earth. Only later did improved observations reveal it was far smaller. Sometimes discovery isn't about something new appearing. It's about measurement sharpening enough to reveal true scale. Perhaps this midnight pulse has been part of Earth's behavior all along, just too subtle for earlier tools to isolate confidently. Historians still argue whether scientific revolutions often begin not with explosions, but with residuals, small discrepancies between prediction and observation that refuse to vanish. You compare archived geomagnetic pulsation data with archived thermospheric density estimates. The correlation appears during multiple solar cycles, though amplitude varies. It's strongest during periods of steady, moderate solar wind rather than intense storms. That consistency brings relief. The anomaly is not unprecedented. It is undercharacterized. You sit quietly for a moment, absorbing that realization. This is not a sudden planetary shift, not a new instability, not an omen of atmospheric collapse. It is a subtle, recurring rhythm, one that modern instrumentation is finally resolving with clarity. And yet, even knowing that, you feel the weight of its interconnectedness. Because the pulse links solar wind orientation, magnetotail reconnection, auroral oval width, ionospheric conductivity, Joule heating, thermospheric expansion, satellite drag. It's an orchestra, and midnight is its cue. Historians still argue whether Earth's magnetic field drift over the past century has slightly altered the geometry of magnetospheric coupling in ways that amplify or dampen such rhythms. As the magnetic poles wander, field line configurations shift subtly. That could change how energy flows during quiet solar conditions. You imagine Earth's core churning slowly, reshaping invisible pathways above. Another archival dataset catches your eye. Airglow measurements from the 1980s. The resolution is coarse, but faint periodic brightening near magnetic midnight appears there too. You almost laugh softly. The planet has been doing this for decades, perhaps centuries. And only now, with a dense web of satellites and ground stations, does the pattern assemble into something unmistakable. A light joke slips into your thoughts. Earth's been running a nightly performance. And when we just upgraded to front row seats. You scroll forward to the present again. The latest midnight line approaches. Right on schedule, density increases. Right on schedule, auroral boundaries widen slightly. Right on schedule, magnetometers twitch. The predictability feels almost soothing, not because predictability removes mystery, but because it reframes it. So instead of asking, what is wrong, you begin asking, how precisely does this mechanism operate? Historians still argue whether the most profound scientific insights come from recognizing patterns that were always there, hiding in noise. You lean back in your chair. Outside the building, the world is quiet. Somewhere, someone is falling asleep. Somewhere else, dawn is just beginning. Above them, the magnetosphere flexes gently. Currents flow. The thermosphere warms by a few degrees. A density increases by a few percent. Satellites feel a slight tug. And then, as sunlight returns, the pulse softens again. You let your breathing slow as you consider the elegance of it all. A planet turning beneath a magnetic shield. Energy flowing in delicate loops. Midnight after midnight, a faint expansion in the dark. Not a crisis, not a catastrophe. Just a reminder that Earth is not static. It is dynamic, layered, responsive, even when the changes are small enough that only the most patient instruments notice. The data continues scrolling softly across your screen, and you watch, calm and attentive, as the next midnight breath begins. Now your attention shifts downward, not into the ocean this time, and not up into deep space, but toward humanity itself. Because whenever Earth's systems show a repeating pattern, someone eventually asks the slightly uncomfortable question, are we amplifying it? A mainstream fact steadies your thinking. Human activity measurably influences the lower atmosphere through greenhouse gas emissions, land use change, aerosol production, and urban heat islands. These effects are strongest in the troposphere and stratosphere, where weather and climate operate. The thermosphere, far above commercial aircraft and storm clouds, seems distant from your daily routines. And yet, it is not entirely isolated. You pull up long-term atmospheric composition data. The carbon dioxide concentrations have risen steadily since the Industrial Revolution, now exceeding 420 parts per million globally. In the lower atmosphere, CO2 traps heat. In the upper atmosphere, however, it enhances cooling by radiating infrared energy into space. That cooling has led to a measurable contraction of the thermosphere over recent decades. So here's the irony. If humans are influencing the upper atmosphere, it's largely by thinning it on average, not thickening it. Still, the midnight pulse persists atop that background trend. Historians still argue whether anthropogenic greenhouse gas increases have subtly altered how the thermosphere responds to geomagnetic energy inputs. A cooler, more contracted thermosphere may react differently to the same Joule heating compared to a warmer, more expanded one. Think of it like stretching a thinner balloon versus a thicker one. The response curve changes. You imagine Earth's upper atmosphere as a finely tuned membrane. If long-term cooling has made it slightly denser at lower altitudes and more rarefied at higher ones, small injections of energy might propagate differently than they did a century ago. Then there's electricity. Human civilization now generates enormous amounts of electromagnetic activity. Power grids, radio transmissions, radar systems, communication satellites. The ionosphere reflects and refracts radio waves constantly. It is bathed in artificial signals. A quirky historical tidbit floats through your thoughts. During World War II, intense high-frequency radio transmissions were briefly suspected of disturbing the ionosphere in measurable ways. Later research showed that while human transmissions can locally modify the ionosphere, especially in controlled experiments like high-frequency heating facilities, the global impact is negligible compared to natural solar radiation. If facilities like HAARP in Alaska have deliberately heated small patches of the ionosphere for research, creating artificial auroras and plasma waves, but those experiments are localized and temporary. The midnight pulse you're observing is global. Still, you check radio transmission intensity logs. There is no synchronized surge in human electromagnetic output aligned with the anomaly window. Global electricity usage dips slightly overnight in many regions, not rises. Historians still argue whether cumulative anthropogenic electromagnetic noise has any measurable long-term effect on ionospheric conductivity. Most evidence suggests the effect is minimal on planetary scales. Nature remains the dominant force up there. You turn instead to atmospheric tides influenced by human behavior. Urban heat islands release stored heat slowly at night. Large metropolitan areas radiate warmth after sunset, altering local wind patterns. Some studies suggest that concentrated human heat output, particularly in megacities, can generate detectable gravity waves that propagate upward. It sounds almost poetic, skyscrapers breathing warmth into the night sky. But when you map the midnight thermospheric pulse, it aligns far more strongly with geomagnetic coordinates than with urban density. The brightest city clusters do not correspond to the strongest density increases. You feel a quiet reassurance in that. Harner Earth's upper atmosphere is not being directly driven by late-night streaming marathons. However, human-induced climate change may still be altering the baseline conditions under which natural magnetospheric processes operate. A cooler thermosphere could mean altered recombination rates, different neutral wind structures, and subtle shifts in plasma transport efficiency. Historians still argue whether future increases in greenhouse gases will continue contracting the thermosphere enough to meaningfully change satellite drag climatology over decades. Some projections suggest that average density at 400 kilometers altitude could decrease significantly by the end of the century. If that happens, midnight pulses like the one you're tracking might stand out even more sharply against a thinner background. You glance at satellite traffic maps. Thousands of active satellites now orbit Earth, far more than during previous solar cycles. Mega constellations blanket low Earth orbit, each spacecraft sensitive to density fluctuations. A light joke flickers in your mind. If Earth wanted attention for its midnight breathing exercise, launching thousands of satellites was an effective strategy. Because with more satellites comes more accelerometer data, more drag measurements, more resolution. Now it's possible that part of what feels like a new anomaly is simply better instrumentation, amplified by the sheer number of orbiting observers. You scroll through atmospheric reanalysis datasets, which assimilate surface weather, balloon measurements, and satellite observations into coherent global fields. There's no unusual lower atmosphere disturbance consistently aligned with the midnight thermospheric pulse. When that reinforces your earlier suspicion, this is primarily a space weather-coupled phenomenon, not a tropospheric one. Still, you can't entirely dismiss humanity's indirect role. By altering atmospheric composition, humans have changed the thermal structure of the upper atmosphere. By launching satellites, humans have increased measurement precision. By relying on GPS and radio systems, humans have made even subtle ionospheric variability economically relevant. The midnight pulse may be natural, but its visibility and its significance are amplified by civilization. Historians still argue whether the Anthropocene, this era of measurable human planetary influence, extends meaningfully into near-Earth space. Most agree that while humans dominate the lower atmosphere and surface, the magnetosphere and solar wind remain overwhelmingly governed by stellar physics. You lean back, feeling a sense of proportion. The sun still drives the largest variations. The magnetosphere still flexes in response to interplanetary fields. Cosmic rays still rain down from distant supernovae, and Earth's molten core still generates the magnetic shield that orchestrates the midnight alignment. Human influence exists, but it is layered atop these deeper forces. Another midnight approaches on the rotating globe. The pulse returns, steady and gentle. Not a signal of planetary distress, not a warning flare. Just a subtle reminder that even in the quietest hours, Earth is engaged in constant dialogue with space. And while humanity may be shaping parts of that conversation, the dominant voices remain magnetic, solar, and cosmic, whispering through the dark long after the last city lights dim. If the magnetosphere is whispering and the sun is behaving, your thoughts inevitably drift deeper, far deeper, into the planet itself. Because beneath the crust, beneath the mantle, beneath tectonic plates and magma chambers, here lies the outer core, a vast ocean of molten iron and nickel swirling around a solid inner core. It is there, roughly 3,000 kilometers below your feet, that Earth's magnetic field is born. A mainstream fact anchors you. Earth's magnetic field is generated by the geodynamo, convection currents in the liquid outer core, driven by heat escaping from the inner core, and the slow crystallization of iron. As this conductive fluid moves, it generates electric currents, which in turn produce magnetic fields. It's self-sustaining, complex, and astonishingly stable over geological timescales, though not perfectly constant. You pull up long-term geomagnetic field data. The magnetic North Pole has been drifting steadily over the past century, accelerating in recent decades as it moves from Canada toward Siberia. The South Atlantic anomaly, a region where Earth's magnetic field is weaker, has been slowly expanding. These are slow processes, measured in kilometers per year and nanoteslas per decade. But could subtle shifts in core flow patterns alter magnetospheric geometry just enough to influence midnight energy coupling? Historians still argue whether recent acceleration in magnetic pole drift signals a deeper reorganization within the outer core, or simply a temporary fluctuation in flow patterns. Core dynamics are inferred indirectly through magnetic field measurements and seismic data. No instrument can directly sample molten iron thousands of kilometers down. You imagine that vast metallic ocean churning slowly, like syrup stirred by planetary heat. If the magnetic field changes slightly, tilting, stretching, redistributing intensity, then field line connections between the magnetotail and the ionosphere could adjust subtly. That might influence how efficiently energy transfers during quiet solar wind conditions. It's not that the core would cause the midnight pulse directly, but it might tune the geometry. A quirky historical tidbit surfaces. In the early 20th century, some scientists proposed that Earth's magnetic field might be generated by permanent magnetization of crustal rocks. It wasn't until the mid-1900s that the dynamo theory gained wide acceptance. The idea that molten metal flows generate a global magnetic shield still feels faintly mythic, like a dragon's heart powering the sky. You smile at the thought. Historians still argue whether short-term variations in the length of day, caused by subtle exchanges of angular momentum between core and mantle, reflect dynamic processes deep within Earth. These changes are tiny, measured in milliseconds, but they hint at a constantly shifting interior. You check rotation data. There's no abrupt change coinciding with the midnight anomaly. Earth's spin remains steady within expected micro-variations. Still, the magnetic field is not static. Satellite missions like ESA's Swarm constellation have mapped fine-scale magnetic field changes with remarkable precision. Small patches of intensified or weakened field drift across the globe over years. You overlay geomagnetic field strength maps with the midnight pulse amplitude. Regions beneath slightly stronger magnetic field intensity appear to show marginally enhanced coupling efficiency. Though the correlation is subtle, it suggests geometry matters. Magnetic reconnection in the magnetotail depends partly on how interplanetary magnetic fields align with Earth's own. If Earth's internal field shifts even slightly over decades, reconnection efficiency patterns could shift as well. Historians still argue whether long-term secular variation of the magnetic field influences space weather coupling in measurable ways. It's an emerging research topic, not yet fully resolved. You imagine Earth's core as a slow metronome, setting the stage upon which solar wind and cosmic rays perform. Above, the magnetosphere stretches and snaps gently at midnight. Below, molten iron circulates, maintaining the invisible architecture. Another midnight sector rotates into alignment. The pulse returns. Thermospheric density rises a few percent. Auroral boundaries widen subtly. Magnetometers twitch. The repetition feels almost geological in its patience. A light joke flickers in your thoughts. If the core is involved, and it's playing the longest game imaginable, but you temper that with caution. Core dynamics operate over years to centuries. The midnight pulse operates nightly. The connection, if any, would be structural rather than temporal. A background condition shaping how energy flows, not a trigger flipping on and off at midnight. You scroll back to magnetic field inclination data at high latitudes, when slight asymmetries between hemispheres appear in pulse amplitude. Small differences that could reflect field geometry variations. Nothing dramatic, but enough to suggest that Earth's deep interior quietly influences how the sky behaves. Historians still argue whether the magnetic field is currently weakening in a way that signals an eventual polarity reversal. Such reversals have happened many times in Earth's history, though not on human timescales. The last major reversal occurred about 780,000 years ago. A reversal would unfold over thousands of years, not overnight. Tonight's anomaly is not a reversal precursor. It is far too gentle. Still, the thought of magnetic poles wandering reminds you that even the most stable-seeming planetary features are dynamic. You lean back and let the layered image settle in your mind. At the center, a solid iron core radiating heat. Around it, molten metal flowing, generating magnetism. Around that, in the mantle and crust. Above, atmosphere layered into troposphere, stratosphere, mesosphere, thermosphere. Beyond, the ionosphere and magnetosphere interacting with solar wind and cosmic rays. And at midnight, along certain magnetic longitudes, a slightly more efficient transfer of energy. A breath, not from lungs, not from weather, but from a planet whose interior and exterior are bound by invisible lines of force. The next midnight approaches, and once again, so the thermosphere swells gently in the dark. You watch the graphs rise, steady and predictable, and somewhere beneath kilometers of rock and molten metal, the dynamo continues turning, quietly sustaining the magnetic stage upon which this nightly performance unfolds. Patterns always feel more meaningful when you realize they've happened before. So you widen the lens, not just across decades of satellite data, but across centuries of recorded skywatching and geomagnetic measurement. Because Earth has a long memory, even if your instruments are young. A mainstream fact anchors you. Systematic geomagnetic observations began in the early 1800s, when scientists like Carl Friedrich Gauss developed magnetometers capable of measuring field intensity and direction with surprising precision. By the mid-19th century, magnetic observatories were operating across Europe and North America, recording daily fluctuations. And they noticed something curious back then: regular daily variations in the magnetic field, even during quiet solar conditions. These were called solar quiet, or SQ variations, driven by ionospheric currents that change with local time. Historians still argue whether early observers fully grasped how tightly those quiet daily magnetic variations were coupled to atmospheric tides and solar radiation. They knew the pattern existed. They just didn't have satellites to map the whole system. Worse, you pull up archived magnetometer records from the early 20th century. Even in the analog squiggles of ink on paper, there are hints of slightly enhanced midnight deviations during certain solar minimum periods. Not dramatic, but present. Then there were the more obvious episodes. In 1921, a powerful geomagnetic storm disrupted telegraph systems and caused auroras visible at mid-latitudes. In 1989, a geomagnetic storm knocked out power in Quebec. In 2003, the Halloween solar storms created widespread satellite anomalies. Those were loud events. Your midnight pulse is quiet. Yet historians still argue whether many subtle, space weather-driven variations between major storms went largely undocumented because they lacked immediate societal impact. Without GPS networks, mega-constellations, and precision accelerometers, small density fluctuations might never have been noticed. You scroll through solar cycle 23 data from the early 2000s. During its declining phase, when solar activity was moderate but not extreme, there are periods where thermospheric density curves show faint local time asymmetries. It's like seeing footprints you missed before. A quirky historical note surfaces. During the 19th century, some telegraph operators noticed that signals sometimes strengthened or weakened mysteriously at night, independent of equipment changes. They attributed it to atmospheric electricity. In a sense, they weren't wrong. They just lacked the vocabulary of ionospheres and magnetotails. You imagine one of those operators pausing at midnight, puzzled by a faint increase in signal clarity, unaware that above him, magnetic field lines were quietly rearranging. Historians still argue whether the Maunder minimum, a period from roughly 1645 to 1715, when sunspots became exceedingly rare, produced long-term changes in upper atmospheric behavior. Direct thermospheric measurements didn't exist then, of course, but auroral records suggest reduced activity overall. Would a midnight pulse like this have been weaker during that time? Or perhaps more sensitive to cosmic ray variations? You can't know for sure, but you do know that Earth's magnetic field and solar output have fluctuated for millennia. The planet has endured stronger storms, quieter cycles, pole drifts, and cosmic ray shifts. And through all of it, the layered system has adapted. Another archived data set from the 1970s catches your eye. Satellite drag measurements during a particularly deep solar minimum show slight density deviations at night. Again, not highlighted in major summaries but visible in raw numbers. It reinforces the growing sense that this is not a new phenomenon. It is an old one, newly resolved. Historians still argue whether scientific blind spots often arise not from ignorance, but from prioritization. Dramatic storms demand attention. Quiet patterns can hide in plain sight for decades. You lean back, on considering how many midnight pulses have occurred while humanity worried about entirely different things. Wars, markets, inventions, elections, unaware of the gentle breathing of the thermosphere above. A light joke drifts into your thoughts. Earth's been doing its midnight stretches for centuries, and we're only now asking if it needs a yoga mat. The continuity is strangely comforting. This is not a sudden destabilization, not an omen. It is part of Earth's normal variability, complex, subtle, interconnected. You glance again at the most recent midnight sector. The pulse rises, it falls, steady, predictable. You begin to see it less as an anomaly and more as a signature of the magnetosphere's quiet mode of operation during certain solar wind conditions. Historians still argue whether, as instrumentation continues improving, you will uncover even finer-grained rhythms, hourly micropulses, seasonal harmonics, multi-year modulations that were once invisible. Perhaps this is only one note in a much larger symphony. The thought feels expansive rather than alarming. Earth is not static. It never has been. Its magnetic field wanders. Its atmosphere expands and contracts. Its auroras brighten and fade. Its oceans rise and fall by millimeters and meters alike. And now, with satellites tracing precise arcs through thin air, you can see a nightly swell in the dark. Not a crisis, not a warning, just a rhythm. One that has likely been unfolding for generations, quietly, patiently, waiting for someone to notice. Another midnight arrives. The thermosphere inhales gently, and history, long and layered, continues turning beneath the stars. Once you recognize a rhythm, the next instinct is to ask the future what it plans to do with it. So you turn to simulations. Because while the planet turns predictably, models allow you to press fast forward. They let you ask uncomfortable what-if questions without waiting decades for answers. A mainstream fact grounds you. Supercomputers now run coupled magnetosphere, ionosphere, thermosphere models that simulate energy transfer from the solar wind all the way down to neutral winds at 100 kilometers altitude. These models ingest real-time solar wind data in geomagnetic indices, solving thousands of equations across three-dimensional grids. They are not perfect, but they are powerful. You feed current parameters into a forecast run, steady but mildly elevated solar wind speed, intermittent southward interplanetary magnetic field turnings, quiet geomagnetic background. The model reproduces something very familiar, a slight thermospheric expansion centered around magnetic midnight sectors. That's reassuring. Then you tweak a variable. What if solar wind speed increases by 20%, but without triggering a full geomagnetic storm? When the simulated midnight pulse grows slightly stronger, Density increases become more pronounced, auroral ovals expand a bit farther equatorward, Joule heating intensifies modestly, still manageable. You increase the amplitude again, this time simulating a moderate geomagnetic storm. Now the thermosphere expands dramatically, density doubling at certain altitudes. Satellite drag spikes, auroras blaze far south of their usual haunts. That scenario is well understood. It's happened before. But your interest lies in the subtle regime, the quiet, persistent pulse. Historians still argue whether prolonged periods of moderate solar wind forcing could gradually amplify such midnight expansions if underlying atmospheric conditions shift. For example, if the thermosphere continues cooling over decades due to greenhouse gas increases, its baseline density profile will change. That could alter how energy pulses propagate. You simulate a future scenario. Lower average thermospheric density, but identical magnetospheric inputs. Interestingly, the relative amplitude of the midnight pulse increases, even if the absolute density remains lower than today. A thinner background makes the pulse more pronounced in percentage terms. You lean back, considering the implications. As satellite constellations multiply, even small relative density changes become operationally important. Operators rely on predictive models to avoid collisions, maintain formations, and manage fuel budgets. When a light joke slips through your thoughts, the atmosphere may be subtle, but satellite accountants are not. You run another scenario. What if Earth's magnetic field weakens slightly over the next century, as some measurements suggest it has been doing? A weaker magnetic field allows slightly more particle penetration at high latitudes. In the simulation, magnetospheric coupling efficiency increases modestly during southward interplanetary magnetic field intervals. The midnight pulse grows fractionally stronger, not catastrophic, just amplified. Historians still argue whether the current decline in overall magnetic field strength is part of a long-term secular variation or an early stage of a polarity reversal. Even if a reversal were underway, it would unfold over thousands of years, far beyond the time frame of these simulations. Still, it's fascinating that deep Earth processes could subtly influence how midnight energy flows from space. And you test cosmic ray variability next. During deep solar minima, galactic cosmic ray flux increases. In the model, enhanced nighttime ionization slightly modifies conductivity patterns, adjusting current flow. Again, the midnight pulse responds, but only gently. The system is sensitive, but not fragile. You feel a quiet appreciation for that distinction. Sensitive systems respond to inputs. Fragile systems collapse under them. Earth's upper atmosphere appears firmly in the former category. Historians still argue whether long-term climate change might alter the altitude of peak thermospheric density enough to change drag climatology for low Earth orbit missions. Some projections suggest satellites may need to orbit slightly lower or higher in future decades to optimize lifespan. In your simulation, the midnight pulse persists across these altitude shifts, its shape adjusting slightly, but its timing remaining locked to magnetic midnight. It seems baked into the geometry. What you imagine the magnetotail stretching into space like a long ribbon, Earth rotating beneath it, midnight sectors passing under a region of enhanced reconnection probability. That geometry will persist as long as Earth spins and the sun blows solar wind, which is to say for a very long time. Another model run explores extreme solar minimum conditions. Quiet sun, steady but modest solar wind, elevated cosmic rays. The midnight pulse appears cleanest in this regime, less masked by storm-time chaos. It's almost poetic. The quietest space weather periods reveal the most delicate rhythms. A final scenario. What if satellite density in low Earth orbit doubles again over the next decade? In the model, more satellites mean more drag measurements, better density assimilation, finer resolution. The pulse becomes easier to track, forecast, and incorporate into operational planning. You sit with that thought. The phenomenon may not intensify dramatically, but your awareness of it will. Historians still argue whether humanity's expanding technological footprint in space will transform subtle natural variability into economically significant factors. When navigation, communication, Earth observation, and defense systems all depend on stable orbits and reliable ionospheric propagation, even small shifts matter. The midnight pulse, once invisible, becomes part of that calculus. You glance at the real-time data again. Another midnight approaches. The model predicts a slight density increase. Moments later, the observations confirm it. Prediction and measurement align. The system feels less mysterious now, not because it is simple, but because its complexity has revealed structure. The thermosphere will continue to expand gently at midnight under certain solar wind configurations. Auroras will widen subtly, satellites will feel a faint tug, and models, refined by observation, will anticipate it more accurately each year. You let the simulation run in the background, its digital Earth glowing softly on the screen. The future, it seems, holds more midnight breaths, but no reason to panic, only reason to keep watching. The more certain you become about the pattern, the less it feels like a solitary discovery. Because NASA is not watching alone. Space is crowded now, not just with satellites, but with agencies, observatories, and research teams scattered across the globe. Data flows across borders as easily as solar wind crosses planetary magnetic fields. A mainstream fact anchors you. International collaboration in space science has been standard practice for decades. Missions like the International Space Station involve multiple space agencies. Solar observatories share real-time data. Magnetometer networks span continents. So space weather forecasting is a global effort coordinated through organizations like the World Meteorological Organization and the International Space Environment Service. You open shared data sets from ESA's swarm satellites. Their high-precision magnetometers confirm the same subtle midnight perturbations. Japanese space weather monitors report similar ionospheric conductivity variations. Canadian auroral imaging arrays detect slightly expanded ovals during the same local time sectors. The pattern holds across independent instruments, independent teams. Historians still argue whether the Cold War rivalry between early space programs inadvertently accelerated scientific collaboration by pushing nations to build overlapping observation systems. What began as competition evolved into cooperation, because space weather does not respect political boundaries. You imagine scientists in different time zones watching the same midnight lines slide across their own hemispheres, comparing notes through emails and shared dashboards. Europe confirms, Japan confirms, Australia confirms. Even amateur radio networks log slightly enhanced nighttime propagation in sync with the anomaly window. A quirky historical tidbit floats through your thoughts. In 1957, during the International Geophysical Year, scientists from 67 countries coordinated observations of Earth's atmosphere and magnetic field. It was during that year that the Soviet Union launched Sputnik, and the modern space age began. The spirit of shared measurement was born alongside orbital rivalry. Tonight's collaboration feels like a continuation of that legacy. You glance at data from Antarctic research stations. Their magnetometers, positioned beneath the southern auroral oval, show the same modest midnight current intensification. The symmetry between hemispheres is striking. Historians still argue whether asymmetries between the northern and southern hemispheres in magnetic field strength and configuration produce measurable differences in energy coupling efficiency. In some events, the hemispheres respond differently. In this case, both show the pulse, though with slight amplitude variations. You compare notes from a European Space Agency briefing. Their analysts have independently concluded that sustained, moderate southward interplanetary magnetic field intervals are enhancing quiet time reconnection rates near magnetic midnight. The phrasing differs slightly from NASA's internal memos, but the conclusion aligns. A light joke drifts through your thoughts. When space physicists across continents start agreeing, you know the data is behaving itself. Meanwhile, private satellite operators are quietly adjusting drag models based on the updated density forecasts. Commercial space traffic management companies incorporate the midnight pulse into their collision probability calculations. It's subtle, but it matters. Historians still argue whether the rapid commercialization of low Earth orbit will force even more precise modeling of thermospheric variability. As thousands more satellites launch, small density miscalculations could compound into operational inefficiencies. The midnight pulse becomes part of that new orbital economy, while you check heliophysics dashboards from upstream solar wind monitors operated by multiple nations. The interplanetary magnetic field orientation shifts slightly southward during each anomaly window, just enough to enhance reconnection. Independent verification strengthens confidence. You sit back and feel the quiet power of shared observation. This is not speculation. It is measured, cross-checked, confirmed. A global network of instruments on the ground, in orbit, at polar stations, even aboard research satellites, has converged on the same conclusion. During certain quiet solar wind conditions, Earth's upper atmosphere expands slightly more than expected around magnetic midnight. Historians still argue whether future missions stationed deeper in the magnetotail will refine understanding of these subtle reconnection cycles. Proposed spacecraft could sit millions of kilometers downstream, measuring plasma sheet dynamics in real time. For now, you rely on the data at hand. When another midnight sweeps across Europe, swarm registers a magnetic twitch, ground stations record increased current flow, thermospheric density rises gently. It is almost elegant in its consistency. You imagine Earth as a hub in a web of shared instruments, each thread carrying a sliver of information, all converging into a coherent picture. The picture is not dramatic, but it is beautiful in its precision. The magnetosphere flexes. The ionosphere brightens slightly. The thermosphere swells. Satellites adjust, and scientists, separated by oceans and languages, nod quietly in agreement. No alarms, no emergency press conferences, just a subtle rhythm recognized, documented, and shared. As the globe continues turning, another midnight line approaches from the east, and across continents, instruments wait patiently to watch Earth breathe again. Once you understand a rhythm, the mind can't resist asking the slightly dramatic question, what if it speeds up? What if this subtle midnight pulse, this gentle thermospheric swell, begins to grow stronger, more frequent, more insistent? A mainstream fact steadies you before imagination runs too far. Space weather variability exists on a spectrum. At one end are quiet time fluctuations like the one you've been tracking. At the other are full geomagnetic storms capable of disrupting satellites, power grids, and radio systems. The physics that drives both is continuous. Differences lie in magnitude and duration. So you explore the edge cases. If sustained southward interplanetary magnetic field conditions were to persist for days rather than hours, without reaching full storm classification, the midnight reconnection efficiency could increase steadily. In simulations, this leads to amplified Joule heating and more pronounced thermospheric expansion. Satellite drag would rise accordingly, somewhat not catastrophically, but enough to require more frequent orbital corrections. Historians still argue whether modern megaconstellations are more vulnerable to moderate, prolonged space weather variability than earlier, smaller satellite populations. With thousands of spacecraft operating in similar altitude bands, cumulative drag modeling errors could compound operational complexity. You picture ground control teams issuing slightly more reboost commands, adjusting trajectories more often, sipping more coffee at midnight. A quirky historical note surfaces. In 2009, during an unusually deep solar minimum, thermospheric density dropped so low that some satellites experienced record-breaking orbital lifetimes. Engineers were surprised, in a good way. Now imagine the opposite scenario, a prolonged period of slightly elevated midnight heating. The difference wouldn't be dramatic, but it would be measurable. You also consider communication systems. If the ionospheric electron density rebounds grew stronger, nighttime high-frequency radio propagation could extend farther, occasionally interfering with frequency allocations designed for typical conditions. Not chaos, just mild unpredictability. Historians still argue whether the growing dependence on precise satellite navigation for autonomous vehicles, aviation, agriculture, and financial systems makes even small ionospheric timing deviations more consequential than in previous decades. Oh, the irony is subtle. The physics hasn't fundamentally changed. Your reliance on it has. You test a hypothetical scenario in your mind, a year of consistently favorable reconnection geometry, steady solar wind, frequent mild southward field alignments, elevated cosmic ray flux during deep solar minimum. In that scenario, the midnight pulse becomes a dependable feature of density climatology. Satellite operators incorporate it into baseline models. Space weather forecasts included as routine. It stops being unusual. It becomes expected. A light joke flickers in your thoughts. Nothing says cosmic drama like a 3% density increase that accountants can plan for. But you push further. What if instead of strengthening gradually, the pulse interacts with a moderate geomagnetic storm? In that case, midnight sectors could experience compounding effects, storm time heating layered atop the quiet time geometry. Yet density spikes could briefly exceed model forecasts by significant margins. This has happened before during substorm clusters embedded within larger disturbances. The difference is that now you would anticipate the geometry better. Historians still argue whether improved real-time monitoring of interplanetary magnetic field orientation will eventually allow near-perfect forecasting of magnetotail reconnection cycles. Current forecasts are good, but not flawless. The solar wind can change character in minutes. You glance at upstream solar wind monitors again. Data streams in continuously, offering about 30 to 60 minutes of warning before conditions reach Earth. Enough time to prepare, not enough to panic. Then there's the question people always ask, even if quietly. Could this escalate into something dangerous? The honest answer, grounded in decades of observation, is reassuring. The midnight pulse itself is a manifestation of ordinary magnetospheric physics operating in a specific configuration. It does not represent instability. It does not signal atmospheric loss. It does not foreshadow magnetic reversal. It is part of the system's normal range. Historians still argue whether public perception of space weather tends to focus too heavily on rare extreme events while overlooking the importance of understanding routine variability. Quiet time physics may lack spectacle, but it underpins everything. You lean back and let that settle. If the trend accelerates modestly, satellites adapt. If it intensifies during storms, operators adjust. If it becomes better understood, models improve. The system remains resilient. Another midnight line approaches. Density rises slightly. Auroras widen a touch. Magnetometers twitch. It feels less like escalation and more like confirmation. You imagine Earth as a vast, layered instrument, tuned to the solar wind's steady breath. Some nights the note is soft. Some nights it is louder. But the instrument itself is stable. A final what if crosses your mind. What if humanity had never built satellites sensitive enough to detect this pulse? It would still be happening, unnoticed, unremarked. The planet would continue its midnight expansions. The magnetotail would reconnect quietly, auroras would shift subtly, and no one would track a few extra oxygen atoms per cubic centimeter at 400 kilometers altitude. Or knowledge doesn't create the rhythm, it reveals it. And revelation, in this case, brings not alarm, but appreciation. As the next midnight unfolds, you watch the familiar curve rise again. Not stronger than before, not weaker, just steady. The possibility of acceleration remains theoretical. For now, the rhythm holds, and Earth continues breathing gently in the dark. By now, midnight no longer feels mysterious. It feels intimate. You've watched it circle the globe again and again, the thin line where sunlight gives way to darkness, where Earth rotates beneath its magnetic tail, where invisible currents intensify just enough to warm the highest air. A mainstream fact rests comfortably in your mind. Earth's rotation relative to the solar wind creates a constantly shifting geometry. Magnetic midnight is not about clocks on your wall, it's about alignment. When a region of Earth rotates into the sector directly beneath the stretched magnetotail, energy transfer efficiency changes. That alignment happens every night, for every longitude. And so does the pulse. You watch the data one more time, not searching for anomalies now, but observing a rhythm you've come to understand. Magnetometers register a faint twitch. Field-aligned currents strengthen slightly. Joule heating increases modestly. The thermosphere warms by a few degrees. Density rises by a few percent. Satellites feel a gentle increase in drag. Auroral ovals widen just a touch. And then, as dawn approaches, sunlight smooths everything back into the daytime pattern. It is a cycle layered atop cycles. Historians still argue whether future generations will look back at this era as the moment when quiet time space weather became as routinely modeled as terrestrial weather. Once upon a time, storms were mysterious and poorly forecast. Now, and meteorologists predict hurricanes days in advance. Space weather may follow a similar trajectory. You imagine a future dashboard where midnight density pulses are forecast as casually as tomorrow's temperature. There's something calming about that thought. A quirky reflection drifts through your mind. If Earth had a heartbeat audible from space, it wouldn't be a dramatic drumbeat. It would be something like this: soft, periodic, persistent. You lean back and picture the entire system at once. At the center, molten iron flowing in the outer core, generating magnetic fields. Above it, the mantle and crust turning steadily. Above that, layers of atmosphere thinning into space. Beyond that, magnetic field lines stretching into the solar wind. And farther still, the sun, steady tonight, blowing a stream of charged particles outward in all directions. Cosmic rays slip in from distant supernova remnants, adding faint ionization. Interplanetary magnetic fields tilt slightly southward. The reconnection occurs in the magnetotail. Energy flows along field lines. Midnight aligns. The thermosphere inhales, and then it exhales at dawn. Historians still argue whether the most profound discoveries are those that reveal not danger, but delicacy. This midnight pulse is not a threat. It is a reminder that even during quiet solar conditions, Earth is dynamically engaged with space. You feel a quiet gratitude for the instruments that let you see it. Satellites tracing arcs through thin air, magnetometers humming in polar stations, radars peering into plasma, altimeters gliding over oceans. Without them, this rhythm would remain invisible. With them, it becomes part of your understanding of the living planet. Another midnight slides across the globe. The graphs rise predictably. You no longer tense when they do. Instead, you watch with something closer to appreciation. Because what NASA is monitoring isn't a looming catastrophe. It's a conversation. A nightly exchange of energy between star and planet, modulated by magnetism, shaped by rotation, softened by dawn. And as the first light of morning touches the upper atmosphere, the pulse fades once more into the background hum of daytime physics. You let your breathing slow, matching the gentle cadence you've observed. Earth turns, the magnetosphere flexes, the thermosphere warms and cools. Night follows day, and day follows night. And somewhere above, in the quiet dark between sunset and sunrise, the planet continues its subtle shift. Steady, measured, and beautifully predictable. Word count, 1012. For a moment, just imagine it from afar. A blue sphere suspended in blackness, wrapped in invisible magnetic threads, breathing almost imperceptibly in the dark. The cities glow and dim. The auroras shimmer faintly wider than usual. Satellites glide through air that thickens and thins by fractions you would never feel. Nothing is breaking. Nothing is failing. The system is simply alive. So you let that thought settle gently. The midnight pulse will come again, and again, and again. Not as a warning, but as a rhythm. A reminder that even while you sleep, Earth is engaged in a quiet dialogue with the cosmos. Subtle, continuous, and astonishingly resilient. You don't need to stay awake to watch it. The instruments will. And tomorrow night, when the world turns once more into darkness, the thermosphere will take another soft, a magnetic breath,